Good afternoon, my name is Rick Schwartz. I'm with the Qualcomm Mobile Computing Group. And today we're here to help you maximize the performance of your software while minimizing power consumption. This workshop is going to be divided into 4 sections. The first is going to discuss the reasons why battery in your phone doesn't always last an entire day. Next, we'll show you how to accurately measure the power consumption of your app and determine whether it has a problem with excess power usage. In section 2, we're going to do a deep dive that shows you how to insert markers in your code to find the cause of power spikes and perform automated testing. After that, we'll present solutions to the most common causes of excess power consumption. Section 3 will show how to do advanced power and performance profiling using the same software all the major OEMs use. This software was only recently made available to independent Android software developers, so chances are you haven't seen it yet. And finally, our graphics and gaming experts are going to show you how to improve your frame rates and optimize your graphic performance. At the end, we have Samsung devices available to be checked out so you can do your own performance and power profiling. And we're going to stick around to answer any questions you have. So that's a good overview. So let's get started. So let's talk about the challenge here. We've seen some mobile trends that make this a lot more challenging. High-end processor speeds have almost doubled over the last 3 years, from 1.5 to 2.7 gigahertz. Number of cores have increased 3 of the last 4 years. Mobile displays are getting much larger and higher in resolution. This Samsung tablet here is a 2.5K display, and lighting up that many pixels takes a lot of power. In addition, mobile devices are now designed to work 24/7. So even though I'm not using my phone right now, it's tracking my location. It's listening for voice commands. I don't have to touch it. If I say, OK, Google, it wakes up, and it's waiting for my question. So 24/7, it's listening for my voice and that keyword. There's also step counters that are tracking my movement, so I can see exactly how many steps I take. All this takes power. In addition, a single mobile processor is doing more than ever. Not only are there 4 or more cores, there's a very powerful GPU inside. Wi-Fi used to be a separate chip. Now it's integrated in the SoC. There's dual image signal processors. There's a floating point DSP. Cellular radio used to be separate. Now it's integrated much of the time. So there's a lot going on in these processors. And the problem, of course, while we've seen this dramatic increase in processor speeds and cores and the activities that are going on, we haven't seen the same increase in battery power. Over the same 3-year period, we've seen a 33% increase in battery power. So that makes all this even more important. When it comes to consumers and what they want to see, battery life is the most important. And it doesn't matter whether they're Android, iOS, or Windows. It's number 1 on all platforms. Carriers have realized that this is a problem, and they've started to publish lists of, they call them high-risk apps. And that's basically apps that drain the battery faster than usual or use excess mobile data. Of the apps that are on the Verizon high-risk list, 70% of those apps are chart toppers in Google Play. So these are some of the most popular apps which have problems. Some of these apps use power 2 to 5 times more than normal. And some of these apps use a lot of excess data. I don't know how many of you have seen the AVG survey that came out this week, but it also flags a number of different apps that have problems with excess resource consumption or excess battery consumption. You definitely don't want to be on those lists. Unsurprisingly, heavy battery usage is the top reason that consumers uninstall apps. And of course, if you have those problems, it's probably not going to help your reviews. So the question that I'm sure some of you are asking yourself is, does my app have any of these problems? And how do I fix them? So one of the things I want to talk about first is how you accurately measure the power consumption of your app. because it's not as obvious as you would think. I'm sure we've all launched the Google Battery app, and typically it shows how much power is remaining, which doesn't really tell you what's going on. So we're going to tell you a very easy way to see exactly how much power your phone's using at any given moment. There's several ways to do this, but today we're going to use an app called Trepn. It's available on the Qualcomm Developer Network. And once you have the app installed, in fact, I'll just follow along here, you're going to launch it, and it has a very simple screen. And we're going to go to Settings, which is in the upper right. And I'm going to go to Data Points. There's a long list of options. And I'm going to make sure that the battery data point is checked, since for now, that's what we're going to concentrate. And I'm going to turn off some of the other things. And it's a good idea that you check a setting. If I go to General Settings, I'm going to check something called Acquire Wake Lock while profiling. What that does is keep your processor awake while you're profiling. If I want to do a 5-minute test, and I want to set my phone down and measure my background, my kind of idle power, the processor is going to go to sleep fairly quickly to save power. And because this is an on-target power measurement app, if the processor goes to sleep, it's going to lose that data, and when it does its average, the average will be either lower or higher than the actual. So it's a good idea checking that section. Then I'm going to hit back, and I'm going to click on Profile System. So at this point, I'm reading the power consumption. If I just want to see the number, I click on the Stats button. And in this particular case, it tells me my phone is using 1.76 milliwatts. Now, one thing we found out is not every device reports accurate power. So there's some that are better than others for this application. If you have a Nexus 5 or a Nexus 7 or a Nexus 4 or an HTC One, you should get accurate battery power readings. And I have some examples on the screen that I've done. So the first one is basically I believe it's a Nexus 5 just idle. So I start the process, I set it down, and I think I ran it for 1,000 seconds, whatever that is. I think it was about 15 minutes. And I found out in that case, the phone was using about 700 milliwatts of power. Now, one thing to keep in mind is when Trepn runs, it's collecting a large amount of data, and it's running on the CPU. It's consuming cycles. So that's one of the reasons that number is a little bit larger than you would expect. But it's all relative, so that's really kind of my baseline power. So that's important you understand that. Then for fun, I took one of the apps on the Verizon high-risk list because I wanted to see, hey, does this really have a problem or not? I happened to be, well, I won't say the name of it, but you can read. And I ran that app for roughly the same duration. I think it was around, in this case, it was 600 seconds. And I found that it consumed 2,388 milliwatts. So that's 3.2 times more power than idle. And one thing that was interesting, that app did turn off after 2 minutes. I ran another app, which you can see at the bottom, which never turned off. So it kept the screen on full power the entire time. So if I was playing that game and I set my phone on my desk and I go to get lunch, for that hour that I'm gone, it's consuming a significant amount of power because the screen never goes off. That's what's called holding a full wake lock, which we'll talk more about later. But unsurprisingly, that app consumed 500% more power than idle and 53% more power than a similar app. So Trepn makes it very easy to determine exactly how much power your app and your system is consuming. It's a good idea you look at idle and real-world use cases. And the nice thing is if you can measure on it, you can act on it. So you can try a certain type of code, a certain technique. You can switch to something else, and then you can, it's very easy to see the comparison. Did you use more or less power? And as I said, if anyone has any questions along the way, feel free to jump in and ask. I already talked a little bit about what to do if your device doesn't support battery power in Trepn. There's some good options available. These are just a few. If anyone has other suggestions, feel free to let us know. On the left, you'll see the Android L battery app. An app that I use a lot is called GSAM Battery Monitor Pro. It's nice because it has a feature you don't see on L, which is you can zoom in and zoom out on the discharge curve. It also shows, if you look carefully, you can see, like the Android app, it shows the screen and Wi-Fi and GPS, different activities. It will also show you temperature and discharge rates. So it gives you a lot of different settings. And then the last is called Power Tutor. Power Tutor uses software modeling. So they're using models, and one advantage of doing that is they can do an estimation on actual CPU power, or you can see Wi-Fi and 3G and GPS. So that's something that's nice. There's a Power Tutor, and then there's a Power Tutor 2. And they're very similar. They seem to do similar things. So let's talk about some best practices for power measurement. One thing that's important, no matter what device you're using, in order to get an accurate battery power measurement, you need to unplug the USB cable, which is common sense, right? Because if you're connected to a computer or you're connected to an AC adapter, the device is charging and you're going to get wrong readings. So it's important you disconnect the USB cable when you're doing power profiling. If you still need USB, you can do that over Wi-Fi, which is nice. As I said earlier, you want to know your device is going to report accurate battery power. This is just a few of the devices that do. We already talked about making sure your CPU stays awake. That will make a big difference in your readings. Another thing which is common sense is you want to minimize the background processes. So it's not enough to go to recent apps and close everything. You're going to want to go, to save time, I'll go to Task Manager. I just clear the memory, and that'll close a bunch of apps at once. And then I also will go to the Apps Manager and look at the currently running apps. And it's a good idea if you want to get the most accurate readings, you're going to close the stuff you're not measuring. That makes a big difference. If you look at the bottom, you can see before closing apps, I did an idle power test, and it consumed 1,043 milliwatts. After closing apps, the idle power, the same exact test, was 726 milliwatts. So those apps that were not in use were consuming 30% more power. So that's something to be aware of. Focus on what you're measuring. Turn off everything that's not related to what you want to measure. If you don't need the radios, go into airplane mode. If you want to measure mobile data, but you don't need Wi-Fi, turn it off. Turn off location, Bluetooth. You'll see later, things like Google Now can consume more power than you'd think they would. You want to reduce the overhead. When I go to the Trepn settings screen, there's a long list of data points. It's tempting to just check everything because you want to collect data on everything. But I've found that it's a good idea. There will be a dialog that tells you not to select more than 6. It really depends what you're testing, but you want to be aware that you don't want to collect more data than you need because it will have an impact on the CPU cycles. Make sure Show Per Application Status is unchecked unless you need to see mobile and Wi-Fi data. And then also, Trepn has a feature called Screen Overlays. You'll see them on the screen. I like to turn those off because it's more graphic intensive, and if you don't need them, don't use them. Be aware that the screen is the single biggest source of power consumption. So if you don't need the screen on, switch it off or put a timeout if you're measuring idle power. And then compare apples to apples. You can't compare measurements on an on-target source like Trepn with an off-target source like a monsoon power meter. You just can't do that. So you want to make sure you're consistent. So let's do another demo here. I want to show how you can use Trepn to profile your mobile processor. If we can get the guys, oh, they're fast, they switched over already. So if you don't have Trepn, as I said, you can go to developer.qualcomm.com. You do have to register, but all you do is put in your email address, and then you'll be able to download Trepn. It's under Increase App Performance. And once you've installed it, I'm going to launch it here. This device has never run Trepn, so we're going to see some recommendations for some changes that you would make. As I showed you before, I'm going to go to Settings. I'm going to check Acquire Awake Clock while profiling, so I keep it awake. I'm going to go to data points, which is in the center. And I can see CPU 0 frequency or 1 are checked. I'm going to add to that CPU 2 and CPU 3. So now all 4 cores are going to be displayed. And then I'm going to go to the overlay screen. And this is how you would see it if you just download the app. I'm going to go to the bottom left-hand corner. And I'm going to change that from bar chart to graph. And I'm going to change it from CPU, hold on here. And then I'm going to go to CPU 0 frequency, and we're going to change that to CPU 2 frequency. And I'm going to turn the thing below it to none. And we're going to say OK to that. And then the last setting I'm going to go is go to the 4th overlay in the corner. I'm going to go to graph. And I'm going to set that to the CPU 3 frequency. Now I think we're ready to go. And there'll be a slide on this in case you want to do it later. OK, now we're ready to do the actual test. It's a good idea if you save presets as you go. So if I want to get back to the factory default, I can save that as default. And then if I want to call this all 4 cores or whatever, you can save those and get back quickly. So I'm back to the main screen. I'm just going to hit Profile System, and then I'm going to touch Overlays. And what I can see here is in the upper left and lower corners, I can see all 4 cores. So when the device is idle, you can see the top 2 cores are fairly busy, but the bottom 2 cores aren't doing too much. That's expected. And then as I launch apps, I don't think I'm on Wi-Fi right now, but as I launch apps, I'll see a big difference in the improvement. So let's say I'm a game developer. I can launch my game. I can play the different levels. And I can see on each level what's happening on each screen. If there's a problem with CPU spikes or GPU spikes, I can see that. Right now I'm showing CPU frequencies, but I can change that to CPU load. I can also display CPU and GPU load on the same screen, along with battery power. So there's 8 different overlays. You can set them to be anything you want. And then once I'm done profiling, I'm going to go to the notification window. I'm going to click on Trepn, and I'm going to say Stop Profiling. So it brings it to the foreground. And then I've got some choices. I can save a CSV, a database file, so I can analyze it later, or I can just say Don't Save. So in this case, I'll save as a database. And it allows me to name it if I want. And then I'll just say Save. Depending on how long you run this, it's collecting a lot of data, so it can take a while to save. So now we've done our first profiling session. If I want to wait till it's done, I can go to Analyze. Oh, there it is. It's done. So now I can go to Analyze Run. I can see the session I just saved, and I can say Analyze it. And I can now look at a different view. This is what's called Graph View. And there's a legend here. And I can pull it out, and now I can turn things on and turn them off. So let's say I just want to care about the frequencies of the last 2 cores. I can easily do that. There's a lot of different ways to view the data, but I just wanted to give you some ideas. Now we're going to switch back to the laptop. There we go. Thank you. Any questions? Yeah, I figured we'd have some questions. If you can wait for a microphone, that would be great.
How do you know which core is your application running on?
Well, Trepn will show you. It's displaying it in real time. So you're going to see, obviously, you're going to see things running in the background as well. There is an option there for profile app as well. But you do have to kind of consider what's happening in the background, which is one of the reasons, like I said, you want to minimize everything that's running on your device that you don't need. That's one of the reasons Nexus devices are nice for profiling, because it makes it. I have a Nexus 7 tablet, which is my favorite device for battery power profiling, because there's very little running in the background. So I can get it where when I go to show the running apps, there's literally like 5 or 6 things on the screen.
So the one in the red was the one that was running that was the core that was running the app.
Yeah, on the test we did, each corner had a different core. So it was core 0, 1, 2, and 3. And You don't know directly which app is running, but as I said, if you go and you make sure that you've shut everything off, all the unneeded apps and processes and services, it makes it really easy to isolate what's happening. And then we're going to show you some other ways that you can actually dig a lot deeper as we get into the presentation. And there was another question, I think.
Yeah, so what's the difference between profile system and profile application?
I'm going to let Eugene take that one since he's one of the engineers behind this, and he can answer it better than I can. We should be able to talk.
So the difference between profile system and profile app. So when you profile a system, that just essentially what you want to figure out is, you want to profile the power or performance of the device itself. When you're profiling an app, the basic difference is that it'll collect some baseline data in the background, and when you select profile an app, it will launch your app. And then there's an option in Trepn under settings called show deltas, and then you can see the difference between the baseline and when your application is running. So that's really the basic difference between the two.
Great. Thank you. Any other questions? All right, we're going to move along here. We got a lot to cover. So I thought it might be nice to show some real-world examples of some different apps I profiled and show you how you can actually use this information in a useful manner. So this is the Trepn graph screen that I showed you earlier, and I profiled an app, and here's kind of a question for you guys. Is this app CPU bound or GPU bound? So the purple line is the GPU load, and the green line is the normalized CPU load for all the cores. Should be pretty obvious, right? The GPU is going up to 100%, a good percentage of the time, and the CPU is actually using 19.48%. So this app is not doing a very good job of balancing the load. And sometimes there's reasons for that. It's probably a game or a benchmark, so there might be a good reason. Obviously, a benchmark wants to exercise the GPU, so there's probably a good reason. But it makes it very clear to see what's happening. Another test I really like to do is see how apps actually balance the load among the 4 or more cores. So right now you can see I've turned off everything but CPU 2 and 3 frequency. And it's pretty common that those are not running very hard. You can see they're almost idle here. The surprising thing is this is actually a very popular benchmark. And it's a benchmark that's actually known for showing multi-core performance. But the reality is it's not showing multi-core performance at all because core 3 and 4 are the cores, the last 2 cores are off most of the time. So it really gives you a view in what's happening. There's software available. Qualcomm has an application framework called Maricors that helps you to distribute your processing load evenly over the different cores. That's something you might want to look into. So it's a way that you can make sure you're using all the resources. One of the nicest things about Trepn is it really is going to correlate the actual power consumption, the battery power being consumed at any given interval with what's happening. So here's another benchmark. This is GL bench. And I have GPU load, which is purple, and then the blue is battery power. And if you look, you can see there's an extremely strong correlation between those two, which is what you want to see. It shows that we're accurately reading the power. You can see battery power does take a little longer to ramp up, which is not surprising, but there's a very strong correlation there. So it's not an estimation here. It's not a calculation. It's actually reading the power management IC and reading the actual power consumed. You can do some interesting what-if scenarios. As I said earlier, you can try 2 different types of code and see what the impact is. Here I used a very popular media player app. And on the first test, I played a 4K video with the software decoder option. And then I ran it again with hardware decoder option. And I found that unsurprisingly, the software decoder used about 3 times more CPU cycles. In fact, you can tell it's pegged. It's at 100% most of the time. And then I switched over to the hardware decoder option. Actually, the green is the CPU loads green and battery is there. Battery was 3,542 milliwatts. On software decode, battery consumed dropped to 2,484 milliwatts. So that's 43% less power consumed. And then, of course, you can also see a big difference in CPU load. The average load on the first test was 90%. The average load on the second test was 31%. So the differences are very clear if you run this tool. These tests are very easy to do. Here's just another question for the audience. Is this app using your system resources efficiently? You can see all 4 cores are almost maxed out, and the GPU is off most of the time. The answer is no, it's not. So if you see something like this, it's a good clue on a potential problem. And of course, it's going to result, in this particular test, battery power is 4,335, so it's 4.3 watts, which is a significant amount of power being consumed. So your battery's not going to last very long if you run this app too long. So up until now, everything we've been talking about is on-target power measurement. Obviously, there's a couple ways to do off-target measurement. Kevin's going to talk about something later called QEPM, which is a way to do off-target measurement with software. And then, of course, a lot of people use hardware meters. You probably heard of Monsoon. They make a meter that you connect to your battery terminal, and it will give you, it will display the voltage, current, and power. It's very accurate. Because it's off target, it's not influencing the load at all. And of course, the downside is it's fairly expensive, and you have to physically connect the wires to your battery. Another downside is it's limited to device power, so you can't isolate it to an individual app, and you can't isolate it to an individual hardware subsystem like the GPU or Wi-Fi or something. We're going to talk about how to do that in just a minute. Well, in fact, we're going to talk about it now. So how can you measure per rail power consumption? It's a bigger challenge. What a lot of the OEMs do is they will actually outfit a commercial device with a bunch of current sensor resistors. So they'll actually take apart a device, and it looks kind of like a Frankenstein. There's a bunch of wires coming out of it. And then they'll connect it to a very expensive box, a box that costs almost $50,000. And it will give very accurate readings. But there's some easier ways to do it. Qualcomm makes reference platform hardware. You can see I'm holding the smartphone. There's also a tablet I have with me. And these have the current, microphone. These have the current sense resistors on the hardware. So they're pre-installed on different rails. So for the Qualcomm Snapdragon tablet, you can measure the power on the CPU rail, camera, digital core, graphics, internal memory, LCD backlight, the SD memory card, the wireless network, and Bluetooth. So most of the major subsystems. And I thought it would be interesting to show an example of this. And we have these devices here, so in fact, I can do it right now. If I click on, I just clicked on Profile System, and then I'm going to go to the Stats view, and you're not going to be able to see this from there, but in real time, I'm seeing the actual power consumption on the different rails. So anyone who wants to play with this afterwards can come up and do so. But to show you an example of a real-world situation here is I thought it'd be fun to do a test where I use the camera in the smartphone. So on the left, I can see what's happening before I take the photo. So unsurprisingly, the CPU and the camera and the graphics and the memory and the SD card are all 0. The reason they're on 0 is because it's showing delta power. So I start profiling, it's looking at the baseline power, and then it's only displaying the difference between baseline and current time. So that's why the CPU is 0. It's obviously consuming power, but because it's factoring in the baseline, it shows a 0. And this is nice because it makes it easy to see the difference between different readings. So if you have different code, you want to see the difference, you can see what's happening on the different hardware blocks. Or in this case, I take a photo. So I took the photo. I quickly try to switch back to Trepn running on the smartphone. And I can see a pretty big change here. So CPU goes from 0 to 651 milliwatts. Camera goes from 0 to 53. The digital core goes up. The internal memory goes from 0 to 126, because once you take the photo, it has to write it to memory. And then SD card, if I waited long enough, that would probably go up. So it gives you a real good advantage on where the power being consumed by your device is going. This is something that isn't available in commercial devices, so you either have to buy a reference platform from Qualcomm or other people who make them, or you have to outfit your device with your own measurement. Any questions on per rail power? Okay, we'll move on. Another question we get is, how do I profile without leaving my IDE? So I'm in Eclipse, I'm coding. I really don't want to leave, especially if I want to see the difference on different types of code. So you can download the slides. It tells you, like everything I'm talking about today, it's all free. It's available from Qualcomm Developer Network. Question in the back?
Can you clarify what does rail mean? I don't know what it means.
Say it again.
What is rail?
What is a rail? Mm-hmm. That's a good question. So basically, your phone has different hardware blocks. So there's the CPU, the GPU, you got Wi-Fi. Each block has its own kind of power rail. I'm oversimplifying things, but it's a way that you can estimate the actual power on a given rail. So let's say I want to see how much power my GPU is using relative to the CPU, relative to the screen. Okay. And once you download and install Eclipse, you're going to see something that looks like this. And in fact, I'm going to switch over to it if I can here. So I'm just going to minimize this and get rid of that. And let's see if we can switch over to Eclipse. Okay, so this should look familiar to some of you, probably most of you. From Eclipse, if I go up here to Perspective, I'll see Trepn in the list, and I select it. And right now it says no devices found, but if I plug in, it should see my device. And if it doesn't, we'll just switch over to something else. This is the one thing I should have tested before. We'll try one thing and see if we get lucky. It needs to load its driver, which, we're getting lucky, yay. Okay, so obviously you need to have ADB set up and working. You need to have a driver for your device, which is a given. So I plugged the cable into my phone. You can see here, it has recognized my device. It's a Galaxy Note 3. It looks like I had started something before, so I'm going to stop that, and then I'm going to start it again here. But basically, you connect your device, and this is, yeah, so it was already doing something. We're going to do it again, though, just to show you. So if I go to the green button that looks like a play button in the upper left, and I'm going to hit that, and it's going to say, ready, configuring Trepn. If you look at status, it tells you what's going on here. And now it says profiling in process. And I should be able to just disconnect this because you want to get accurate battery power. And so now I can go and I can do anything I want on my device. I can go and I can take it and I can use a cellular radio, I can use Wi-Fi. Just use it like normal. When I'm done profiling, I will plug it back in. And I got some stuff running in the background that I think is not helping us here. Yeah, it's funny. It's not seeing. Let me see if there's a message in the background here. I think it has something to do with my browser window being stuck. But basically, it's very easy to do on your own. You just hit the stop button, and then the data will load on the screen. Now, I think it has, yeah, okay, so it's seen the device. So we're going to do that one more time. I'm going to click on stop. You can see the big red button. So now what's going to happen here in just a minute, it's going to transfer all the information it's collected, and you should see that appear on the screen. There it is. So I wasn't doing anything very interesting here, but I'll show you an example that I think you might find a little more interesting than just my phone sitting here. I ran this last night actually as I was leaving the office here, and it really shows you what you can expose and see. So you can see there's colors on the left that shows what the different charts are. So at the top I can see what's happening with the CPU. Below that there's GPU. Here's my screen. In the office, my screen's set to about 50%. When I go outside, I turn it up to 100%. We can see that. And then I change it as I go. Here it shows I'm on Wi-Fi in the office, which is no surprise. And once I leave the office, I can see it switches over to the cellular radio. And here I can see exactly what the radio is doing. So I can see what state it's in, whether it's transmitting or idle or dormant. And I can also see exactly what's happening. So here I can see, it looks like I loaded Google Maps. You can see the data that Google Maps is sending. I can see here as the map loads, there's CPU spikes there. Below that, as I scroll the map and pinch to zoom, I can see the GPU kind of spike up here. Here I can see the GPS. Google Maps is doing a GPS fix. A little bit later, let's see what we see here. Looks like Twitter here. I launched Twitter. You can see the data it sent. Unsurprisingly, Twitter also throws a GPS fix. So it's almost like a way to look into your phone and see exactly what's happening. If you have an Android 4.3 or earlier device, it's going to show you wake locks and Wi-Fi locks. That shows you exactly when an app is keeping the processor awake or the screen awake. And it's very useful because it will show which app, how long, and you'll tell from the activity whether there's a good reason you're waking up the processor. If I'm using the phone and I'm launching something and I'm engaging, obviously that's a good reason. If the phone's sitting on my desk, probably not a good time to be waking the processor a lot. Any questions on it? Oh, here you can see I turn on Bluetooth and I start streaming music. So GPU goes literally to 0. You can see the CPU drops way down. Here you can see I turn my display off completely because my phone's in my pocket. So it's very revealing. And I think you'll find this interesting if you try it with your own apps. Any questions on this? Question in the front?
So for the Eclipse application, is it possible to have multiple devices connected to the same IDE, or are you limited to just one?
I'll let Eugene take that question. I think you can have multiple, but I haven't. You can only do one at a time. We're going to show you after this, we're going to show you an advanced profiling tool that will let you profile multiple devices at the same time. So let's say you had 2 different Samsung phones and you wanted to compare them in real time. Or you could have a bunch of different phones running different software. So in real time, you could compare KitKat with L-Release. And Kevin's going to talk about that after we're done here.
Okay, thank you.
I just need to figure out how to switch back here. Yes?
So on those graphs, what was the y-axis, and can I see how many bytes were transferred?
Yes, you can. So the question was on the graph, what's the y-axis? So the y-axis, I believe, is time.
And the x-axis.
So the x is time, and the y is the amount of data transmitted. And it shows you send and receive, and it will show you actual bytes or kilobytes. So you'll see every app, sent or received, how long, how much data. All right. We've already covered this.
Got another question.
All right, we gave the plugin demo. It looks like we have another question.
Quick comment.
Yes.
I signed up for the developer access.
Yes.
You have to copy and paste the link. Didn't work in Explorer 11. Works in Chrome.
Oh,
So if
interesting.
guys are trying to pull it now and install
Okay,
them.
that's good to know. Thank you for sharing that. All right, moving along.
I have another question.
Yes.
This tool seems really useful, especially all the graphs and the details from the high level to the low level. My question is this going to work for any Android device, or is this only going to work for Qualcomm
That's a great
processor?
question.
And if it is Qualcomm, is it also going to work for the smartwatches that run on Qualcomm processor?
Yep. So first of all, the tablet I demonstrated first is a Samsung Galaxy Tab S. There's two versions of this tablet. One has a Snapdragon and the other has an Exynos. The version I showed is actually in the Exynos version. So even though it's not a Snapdragon device, we still saw all the CPU metrics. So obviously, if you don't have a Snapdragon processor, there's certain things we can't get, like the GPU stats. So it'd be GPU load, GPU frequency. For some reason, screen, was it brightness or, yeah. Screen brightness wasn't displayed, but all the other relevant CPU apps were displayed on this device. So Trepn will run on any Android device running 2.3 or later. So obviously, you're going to get more information on a Snapdragon device just because there's information we can get to that we couldn't necessarily get to on other devices. But it's still pretty useful.
Do you know what the smartwatches, like the Android ones or the Tizen ones, are they based on Qualcomm?
Yeah, so I'm wearing a Galaxy Live here. I believe every Android Wear smartwatch except the Motorola, I think is it the 360? That's a TI chip. But most of the smartwatches are Snapdragons. The Gear Live, the LG, there's a couple LGs that are Snapdragon. There's an Asus that's Snapdragon. The Tizen, some of those are Exynos, but the Gear Live is a Snapdragon processor. And we are looking at special tools for, there's ways you could do it now by sideloading and doing things, but we're looking at the possibility of creating special tools for profiling wearables. Okay? Another thing you can do with Trepn, either the standard APK or the plugin, is to see what's happening when your device is idle. So I don't know about you, but if I look at the 4G thing on my phone, I'll see those up and down download arrows light up, which always kind of makes me curious because I'm not using my phone, yet someone's using it. So I was curious to know who's using my phone and what are they doing with it. So I set my phone on my desk, and I actually started Trepn first, and I set it on my desk, and I leave it there for 3,500 seconds. And what I found was pretty interesting, and you can do this on your own, but I found that there was a lot going on. So this is the actual data that's being transmitted, and this is the cellular radio. So my phone is idle. There's nothing that I'm using it for. Yet the radio was in a full power transmission here for about, looks like at the beginning, looks like about 200 seconds. And then you can't see it because I have some other things on the screen, but it's going off and on throughout the period. And even in this quote-unquote idle state, it's still consuming 150 milliwatts of power, which is a significant amount of power. So my phone's idle, yet it's actually consuming a lot of power. And I was curious to know which apps. There's a lot of apps down there, and there's a lot of data being transmitted on the cellular network. All those little lines on the bottom are data packets. And if I launch that in the actual app here, which I'll be happy to do afterwards if you want to come up, you'll see exactly which app is transmitting the data. But I noticed Google Search was appearing a lot, which I thought was interesting because I'm not actually using it. And then I started thinking, well, wait, I did I use Nova Launcher, and I did turn it on where it's always listening. Even if my lock screen's on, it's always listening. Well, it comes at a price, right? Because it's always listening, and I don't know if the analysis is cloud-based. It kind of appears it might be. But regardless, I noticed that a lot was going on there. I also noticed that at least 3 times there's apps that are doing GPS fixes. So even though it's idle, people are collecting information. I assume it's analytics, which is very common. So apps are running and they want to know where you are and what you're doing. I was a little more surprised that I saw the GPU working, and not just working, but working pretty hard. And then the biggest surprise was actually the CPU activity. So this is load, and you can see it's very active. In fact, it never goes to sleep. Not even for 1 second does it go to sleep. So it's active the entire time, and at some points, all 4 cores are active. So my phone is idle, yet all 4 cores are active. So then I wanted to see, well, what's happening here, and who's using this data? Now, this is just one test, and this is just a 15-minute interval in time, and it's my phone, which is probably not representative of other things. But I found in this particular test, I went back to the Trepn screen for this. As I kind of suspected, mobile data usage, Google search was number 1, Exchange was number 2. So it's trying to sync my messages and things. Twitter was number 3, which was surprising because I didn't actually use Twitter. Facebook was number 4. I never used Facebook. Google Play Services, I never used, but it was number 5. And then Wi-Fi data. Wi-Fi is less concerning because you can see Flowly is transferring a bunch of articles, pre-downloading articles to my phone, which is useful. And frankly, as long as I'm plugged in on Wi-Fi, I'm okay with that. And then CPU usage by app was also kind of surprising because you can see S-Health, which is a good app I really like. But when my phone's idle, I was surprised it was using 30% of the CPU. So interesting. And then I kind of zoomed into some of the data because I really wanted to see what happened. And I had a theory, well, if it says Google search is using a lot of data, I wonder what would happen if I turn off Google Now, which I did. And you can see the before and after. So dramatic reduction in traffic. And again, it's just doing what I told it to do, which is listen all the time. So that's what it's doing. But there is an impact on not only the processor, but battery life. And then another thing that you can see in Trepn, and there's another really useful tool I'd like to encourage everyone to check out called AT&T Aero. It's even better in terms of cellular radio analysis. It's free, and you can download it and try it, but it shows similar things. And the question is, are you using the radio in an efficient manner? So here I can see, even though my phone is idle, at this moment in time, there's a UVerse app that's downloading a programming guide. So I do happen to have UVerse, and I do like to get updated TV, but probably better not to send that data when I'm on cellular. They could have easily said, hey, let's wait till the person's on Wi-Fi. Let's wait till he's plugged in and charging, and then I'm going to transfer this big program guide. So those are easy things to do, and this app will show you if you have these problems. The orange data is when the data is being received. The darker orange is when it's being transmitted. You have control on when it's sending, and you can see there's a bunch of little lines that are a couple seconds apart. That's a great example where if you group that data together, it's much more efficient. And let me show you why this is such a big deal. We talked earlier about the radio. So a dormant cellular radio consumes about 10 milliamps. In fact, in the newest phones, it's probably more like 4 milliamps. Almost no power. The difference between system idle and the radio idle, there's almost no difference. They're extremely efficient. So you want to be in that dormant state. When you're in full power transmission, either receiving or transmitting, it jumps up to an active state where the radio is consuming 250 to 300 milliamps. That's a lot of power, especially if the radio never gets out of that state, which in the tests I showed was the situation. It was always either in full power or the next level down, which is the 150 milliamp power. And if you don't use it efficiently, you're going to find that they call it long tail. You can see, even though I send 1 byte, it still has to bring that radio up. It's still going to stay up for 8 to 10 seconds. And then it takes 8 to 15 seconds before it can get down to that low power state. So you want to be very aware of how you're using the radio. Any questions? Okay. At least now you know. See, it's not surprising to me that a lot of apps have a problem with this because most developers don't know how to tell what's happening and how to see what's going on. Once you can see what's going on, it's actually pretty easy to address the problem. So how do you efficiently use the cellular radio and Wi-Fi network? Here's a couple tips that I would give you. One is connect less often. After you transmit data, radio is going to stay on 10 to 12 seconds, so be aware of how often you transmit. Push, don't pull. Specify how many items are delivered. If you're going to use analytics, be aware that different analytics there's big differences in performance, the amount of data they use and the amount they transmit, so be aware of that. Use them wisely. Capture your data locally, group your transmissions, extend the time between transmissions. Offer ad-free versions of your apps. Apps without ads are going to connect to the network a lot less often. Don't continually scan. Create timeouts appropriately. Don't continually stream in chunks. And then offload to Wi-Fi. We talked about the program guide example. Not only is it going to use less battery than 3G or 4G, obviously the amount of data that you consume is important to consumers. There's something new that not everyone probably knows about, which is the new job scheduler APIs in Android L. These are a very effective way of grouping your data efficiently. And there's a new tool that you might want to check out called Battery Historian that basically records log data and it will display it in a nice chart. And it gives you insight on your wake locks and your mobile data usage. So here's an example of the Battery Historian screen. And just an example of how Job Scheduler can improve the situation. If you look at the top line, the before line, right there, you can see there's a lot of packets. This is not unlike the Trepn plugin chart I showed you. In fact, there were even a lot more packets in the chart I showed you. And then here, after using Job Scheduler API, you can see the packets. There's more grouping of data. There's bigger gaps, so this gives the chance the radio to drop down in that efficient state. So it's a much more effective usage of the radio. Here's another example where I have 3 packets at the top, different sizes. The orange line is how long the radio is active. So with 3 spaced packets, you can see how much longer the radio is active than if I basically line up these packets and send them all together. So that's going to result in savings of power. In fact, the power savings can be significant. In this particular example, almost half the power was consumed. All right, now we're going to do a deep dive in some stuff from Eugene. Before that, it looks like there might be one more question.
What about the radio, like turning the radio, like bringing it on and off with those gaps you were showing? Is that like effective? Because the radio also takes time to turn on and turn off, right?
It does, although it's pretty efficient. There is a ramp up, you're right, but it's not really a problem. The processors do a very good job of doing that. But you do have the ability to close a connection versus just letting the connection time out. And simple things like that can save a ton of power. All right, now Eugene's going to take over here.
There's one more question.
Okay.
So is there overhead of your tool in the phone itself? I mean, does your tool, the profiling, consume power?
I didn't hear the question. Say it one more time.
Does the act of profiling in Trepn consume power, and how much percent is that?
Very good question. Yes, as I said earlier, any on-target profiler is going to consume CPU cycles. We're creating a new version of Trepn plugin for Eclipse that is more of a streaming version that's going to consume less resources. There are other ways to measure power off-target. And later in the day, Kevin's going to talk about a tool that's off-target. We'll that will have almost no impact on resources. Okay, we're going to switch over.
All right. Hi, everyone. My name is Eugene Kalinko. I'm a senior engineer at Qualcomm. And actually, I'm a software engineer on the Trepn profiler tool. So today, I'd like to talk about two advanced level features in Trepn that you can use to profile your apps. The first one I'll be talking about is called application states. And the second one I'll be talking about is Trepn's automation features. And if at any time you have any questions, please raise your hand and I'll be happy to answer them. All right, so the first feature I'd like to talk about today are application states. Now, what are application states? Application states are markers that you can insert in your code to identify causes of CPU, GPU, and power spikes. So the typical use case for this is if you're working on a mobile app and you'd like to figure out, you're seeing some power spikes and you'd like to figure out where in the code it's happening. So how do you actually go about doing that? So it's a two-step process. The first step is to actually insert these markers into your code. And here on the left, you'll see a little code snippet that shows you exactly how to do that. So let's just go through it step by step. So in the first line, you create a new intent. What an intent is, it's a message that Android uses to send information from one application to another application. In this case, we'll be using an intent to send the application state from your app to Trepn. For the second line, you'll actually be populating this message. So for the second line, you need to add an integer value that you will use to track your application state in Trepn itself. For the third line, there's an optional description you can give as well. Once that's done, you go ahead and use an Android application context to send the message to Trepn. Trepn captures that, and you're able to plot it similar to what you see in this graph on the right. So if you take a closer look at this graph over here, you'll see that Trepn is capturing 3 different application states. Application state with value 2, application state with value 7, and application state with value 9. So the great thing about this is that besides just plotting application state, you can plot other system level data right alongside it. So in this case, we're plotting battery power right next to application state. So you're able to synchronize. You can see what your app is doing is how it's affecting system resources. So let me kind of go a little bit deeper into this and give you a little example. So in order to showcase this feature, we developed an app. It's a simple browser app that basically runs through the following things. So it loads a page at random, scrolls very quickly down to the bottom, and then idles for about 5 seconds, and then loads another page. So basically how I typically browse the internet. So in this application, we've inserted, there's 3 clear states. There's the idle state, then there's the page load state, and then there's the scrolling state. So we've instrumented this app with 3 different markers that you can see on this graph over here. So you can see this marker over here is when your application is idle. So you can see that when it's idle, there's very little battery power being consumed. In this second state, you can see this is the marking for when your application when the browser is loading a page. And you can see that the battery power consumption is significantly higher. And in this third state, this is when you're scrolling down to the bottom of the page. And you can see the battery power consumption here is high as well. So if you're looking to optimize your app, you would take a look at these 2 code sections. And then later, Rick will provide some tips regarding some common problems that you see, that you typically see, and how you can resolve them. So hopefully the cases you're able to resolve these problems, you run Trepn again, and you no longer see these 2 spikes. So one kind of hidden feature you might not see right away when using application states is if you just imagine for a second we did not plot application state on this graph. And if you look at that power spike marked with number 1, it's the red circle on the very left. You might think that that spike is being caused by your app. But when you use application state, you know that your app was idle at the time. So it's probably something else in the system that's causing it. All right, so that's how you can use application states in your code in order to find any CPU, GPU, or power spikes. Are there any questions on this? All right, so let's move into the next Trepn feature, and that's automation. Now, well, what do I mean by automation? What I mean by that is Trepn has built-in functionality in it that allows you to control Trepn within an automated testing framework. So one example of this is if you have your device connected over USB to your PC and you're running a batch script. So let me give you an example now where this kind of feature is useful. So we decided to showcase this feature, we decided to run an experiment. And in this experiment, we want to find out one simple thing. How is device battery consumption affected by frequency scaling? And if you don't know what frequency scaling is, it's a feature that basically all modern CPUs today that they use in order to balance power versus performance. And the way they do that is they have a stepwise function for the frequency. And each of the CPUs can take any of these frequencies. For example, the CPU we used here is able to clock at 300 megahertz, 422 megahertz, all the way to 2.27 gigahertz. So it's a well-known fact that the higher your CPU is clocking, the more battery power it uses. But the exact behavior is not clear, and it actually varies from different CPU manufacturers to algorithms present on the CPU. But if you were to just take a look at this, you might think that the relationship is linear, and you might ask yourself, well, how much power is consumed when my CPUs are running at the highest frequency versus the lowest frequency? So you can use Trepn's automation features to figure that out. And here's how we did that. I'll be going into a little bit more detail for this in the next slide, but kind of the basic principle of how we did this is we set the CPU at the lowest frequency, and then we slowly scale the CPU up, and then measure the battery power. Now, in order to measure the battery power just at that frequency, we used application states. And if you run through this experiment, what you'll get is, and you'll open up the session in Trepn for analysis, you'll see something similar to the screenshot on the left. And you can see that the statistics screen is separated into different statistics for each application state. So for example, on the top left, we have the statistics for 300 megahertz, which is around 3,050 milliwatts, and so on and so forth, and until we get the statistics for the highest frequency. Now, if you take that data and then you plot it into in bar chart format, what we have on the right, you get to see some interesting relationships. So as I mentioned before, the basic relationship is you increase frequency, your battery power is increased as well. But what you may not have been expecting is that if you look at that bar chart, the relationship is actually not linear. It's a different. And another interesting thing to note is if you compare the battery power consumption at the highest frequency, 2.27 gigahertz, with the lowest frequency, is you'll see that your device consumes 60% more power when all the CPUs are at their highest frequency. So you can really see how this frequency scaling feature is really great at balancing power versus performance. All right, are there any questions?
That's a good point about power versus performance. Let's say you wrote a code and it's, the code is performing well, but it's consuming more battery. Then how do you do a trade-off that you write like a algorithm that's slower but it uses less battery? I don't know, maybe I'm not clear on my question, but I'll ask a better question later. Maybe I'm not clear.
How can the application control the frequency of the
Let's do one at a time.
Yes.
Let me just quickly address the first question, is that it's really dependent on your app, what the algorithm is, and see how you can, like you mentioned, slow it down. Sometimes you may not need to slow it down, but you can still get great power power versus performance.
Yes, I think perhaps what the first person had in mind, a similar question. If you get only a 60% increase in power consumption, but a 10-fold increase in processor speed, right? It seems like, this is perhaps a very naive question, but wouldn't we be better running at top speed if we have a lot to get done? Am I clear on that? Because obviously it's much more efficient in terms of computations per battery power when you got the CPUs cranking. It's very inefficient at the low frequencies.
I want to comment on that.
Yeah, you understand the question.
I do, if my mic can turn on. So if you were paying attention earlier, I showed you the one chart where the one app was running the processor at 100% and was using 4.3 watts of power, which is a crazy amount of power. There's several different options you have. One is, in that particular case, the GPU was basically idle. So anytime you can offload from CPU to GPU, it's going to make a difference in power. And we have some people that are going to be talking about GPU and also how you can optimize to more effectively use the GPU. We're also going to talk a little bit later about offloading to the DSP. Every Snapdragon processor has a DSP, even the wearables. And when you do that, it's a dramatic reduction in power. So it's a very good question, but we're going to talk a little bit more about it later.
So then the notion. 1, 2, 3. So the notion of efficiency here, it would be naive to say it'd be better running with the processors maxed out because you get more instructions per watt.
Well,
You see, so you're saying, okay, we can offload to a specialized subprocessor, of course. But just running on CPUs seems like you get more done per watt at the high frequency settings. Now, is that just apparent or is it not really
It really depends on the type of task.
Oh, okay.
And as I said, we'll talk a little bit more about that later. Thank you. Yep.
So these graphs, are they plotted in a continuous load, or is it for a fixed load, and how much energy does it take? That's the first question. And second is, you said that the power is not scaling linearly with frequency, and that is seeming little counterintuitive to whatever we've learned so far. So,
all right. So there's 2 questions to this. So the first question is, how does CPU load basically factor in all of this?
do you have a constant CPU load going on when you characterize this? Or is it do this 100 instruction, or do this continue looping this?
So the key kind of to this is that CPU load is not relevant here. So it doesn't. So if you set your processor to a specific frequency, it doesn't matter what the CPU load is. It's using the same power. So if there's no load, it's just wasting those cycles. If it's 100% load, it's using the CPU 100% efficiently, right? But the power stays the same. The power is only dependent on the frequency itself.
But if there is no load, then the frequency is irrelevant because CPU is just going to idle out. It's going to be clock gated and it's not going to do anything.
Well, the thing about CPU load, right, is that I mean, like even if you're running at like 300 megahertz, you're using all those clock cycles, but the CPU load is how many of those clock cycles are actually used versus no ops basically. Yeah.
We should move on.
Okay. All right. I think we can discuss more of these questions after the presentation. It's going a little bit more into detail. So let me go into a little more detail of how you can actually capture this data in Trepn. So the basic setup is this. We have an Android device, and the device has to be rooted. And that'll answer actually one of your questions. So in order to frequency scale the CPUs, you need to have a rooted device. Otherwise, you do not have permissions to do that. We connect the device over USB to a PC. And on the PC side, we run this script. So, and then if you follow along with me on the script, so the first step is that we need to start Trepn. Our second step is that we need to start profiling in Trepn. And then there's a parameter to save that, to save the session as a database file. And that session we open later for analysis. Once that's done, we send an application state to indicate that we'll be going to the lowest frequency to start with. And then we actually scale the CPUs. The way we scale the CPUs is we set the minimum bound and the upper bound for each CPU to the frequency that we want. And we do that for all 4 CPUs. This is a quad-core device that we tried this on. Once we do that, we sleep for 30 seconds. For 30 seconds, Trepn is collecting power data for that specific frequency. And you can see that if we make this, if we sleep for longer, we can get a bigger sampling interval, and hopefully that gets us more data, more accurate data. So once we profile for 30 seconds at that frequency, we go ahead and repeat steps 3 through 5. We send an application state to indicate we're going to be scaling up to the next frequency. We scale up the frequency, and then we collect data. And we keep scaling up the frequency and collecting the data until we get to the maximum frequency. And once we've collected the data for the maximum frequency, we go ahead and we stop profiling. And as a result, we get something like this graph. You can see that there's a lot of noise in the battery power, so there's other things running on the system. So you can see from the previous slide the benefit of using application state in this kind of example. You can get the average battery power for each frequency. And one of the groups that really loves to use the Trepn tool is actually researchers and graduate students. Because if you've ever tried writing a paper for a conference or a journal, you'll know that one of the hardest things, one of the challenges in doing so is actually getting the data. And if you use Trepn's automated testing features, it makes it really, really easy to get the data. All right, so today I talked about 2 features in Trepn, 2 advanced level features: application states, which are markers that you can put into your code in order to identify CPU, GPU, and power spikes, and automation testing, how you can control Trepn within an automated testing environment. So, but as I promised, now I'll take it over to Rick to talk about common causes of excess power consumption.
Thanks, Eugene. I think we're going to hold on the additional questions because we have 3 excellent speakers coming up, and I want to make sure they get all the time to present. and then we can take questions at the end. So I'm going to go through this quickly here. So we already talked about this earlier, the 4 most common causes. Wait, how did we get out of? Okay. Okay, yeah, I guess we didn't. Okay, so we've got number 1, preventing the processor from going to sleep. Number 2, keeping the display awake too long. Number 3, inefficient use of the cellular radio. And number 4, taking too many GPS fixes. And we've seen all those in some of the demonstrations today that we showed. So there's a couple ways to tell if your app is keeping the processor from going to sleep. One of my favorite ways is an app called Wake Lock Detector. And it runs on any Android device 4.3 or earlier. Unfortunately, if you have a 4.4 L release, you're going to have to use something like Battery Historian. But it's very easy to use. You run it, you unplug your device, let it run for 2 to 3 hours, and it's going to tell you the duration of wake locks held. In this case, Exchange Services was number 1. Rhapsody was number 2, which is a music service which wasn't in use, yet it kept the processor awake 6 minutes. And then it also shows you the number of triggers. So even though Facebook didn't appear in the top, looks like it was about 10 on that list, it was number 1 in terms of the number of times it woke the processor. In this particular case, in a 4-hour period, it woke it 192 times, even though the person never launched Facebook. It was working in the background. A year ago, I ran the same test, and I found that Facebook woke the processor over 1,000 times. So they've actually made some big improvements in that app, but still it's number 1 in this particular test. So this is easy-to-use software. It's very easy to, obviously you'd rather not your app be on any of those lists, but it's a good way to tell. Why this is such a big deal, I don't know if any of you saw the paper that Google did at I/O this year on Introduction to Project Volta. But they looked at 3 popular use cases. 1, keeping the application processor awake. 2, the cellular radio. And 3, the screen on. You can see how much power the radio uses because of that long tail, which is the red part of the graph. And then you can see, even though the screen turning on is relatively short, it's a very large power spike. They found that kind of profiling with these 3 use cases, even though a Nexus 5 in standby would work for a month in standby, of course in real usage, it's hard to get through an 8-hour day. And the reason is, every app, for every 1 second of activity, that consumes 2 minutes of standby power. Now that in itself isn't a problem, but the problem is the average consumer has 25 to 50 apps on their phone. I have probably 150, and I'm sure there's people in here that have more. So you start adding up all those individual apps and all that activity, and in their particular example with 50 apps, 100 minutes of power is consumed every hour, the equivalent to that. So over an 8-hour period, a lot of power is consumed. And that's why those long standby periods get eaten away. There's some easy things you can do to basically avoid keeping the processor awake. Don't acquire wake locks unless you really need them. Use the minimum levels. Release them as soon as possible. If you need to wait to light the screen, use the flag keep screen on command. Consider using the alarm manager in situations where you want to have the application code run at a specific time. One reason for that is beginning with KitKat, the OS will shift the alarms to minimize the wake-ups. And then, of course, for normal timeouts, it's efficient and more efficient to use Handler. So I know I'm going fast, but all the slides are available. You can go through this after the fact. Wi-Fi locks are pretty much common sense. Obviously, you don't want to hold them unless you need them. There are some situations where you would want to hold a Wi-Fi lock. Let's say the person's doing an app download or a big file download. That would be an example where you'd want to keep the Wi-Fi network awake. In real usage, I find the Wi-Fi network really never goes to sleep. So someone seems to always be keeping it awake. So I wouldn't worry as much about that. With GPS, obviously you want to be aware of when you're taking fixes. If you can use a coarse fix, it consumes about 1/10 the power. Let Location Manager find the best provider. Put a timeout if you can't find a satellite so you don't use unnecessary power. Make the user aware of when you're tracking them, and make it easy for them to disable that. We talked a little bit about DSP. Anytime you can offload from the CPU, generally you're going to save power. GPU is much more efficient for certain activities. DSP is very efficient for other types of activities. Here we have an algorithm which does facial detection. And you can see the difference between the CPU utilization. CPU versus DSP uses 52% CPU when you port it to DSP. The same algorithm actually detects 7% less time and consumes 30% less power. Here's another good example. Offloading audio to DSP is very effective. Android 4 has some audio tunneling that will make this easy to do. And using that tunneling, you can get audio playback for up to 60 hours. And that's a 50% increase over playing that same audio back over the CPU. So it's easy to do and it's very effective. One of my favorite demonstrations is something that actually affects me personally. I track my sleep using my Android wearable. And the upside of this is you don't have to set, with most sleep tracking, you set the phone on the bed and then you leave it there. And of course, you pretty much have to have it plugged in or it's going to drain the power. With this, it uses the gyroscope in the wearable. So my first concern was, wow, I used to charge my wearable all night. What's going to happen if I use it all night? And I found I could use it all night, so I'm doing 8 hours of tracking. It's tracking every movement. And I wake up, and I still have 70 to 80% power left, which is amazing. If you don't use the DSP, for example, if you try the same thing with a Motorola 360, which is not doing what's called sensor batching and using the DSP, when you wake up, the device will be dead. It will use 100% of the power. If you try the same thing with some other phones on the market, it's going to use 70% of the power. So it's easy to do. Basically, what's happening is the DSP is collecting the gyroscope data, and then it's basically collecting it with the processor completely shut down. And then once the processor wakes up, it's going to basically provide a batch of that data available. So it's easy to do, extremely effective. So recap. Sorry for going so fast, but I want to make sure the other guys get all their time. Use wake locks only when necessary. Use the minimum level possible. Release them as soon as possible. And use the keep display on instead. Close your TCP sockets when done. Otherwise, you're going to bring up the network just to tear it down. That fix can save 20% power. Group your network activity. Be flexible in your ping times. AT&T has some really good best practices. If you try their Arrow app, not only will it profile your app, but it will give you best practices and tell you what you can do to improve things. And if you click on it, it will give you a lot of information, very detailed information on what you can do. Obviously, you want to turn off things like GPS, camera, accelerometer when you're not needing them anymore. And my last slide, long battery life is very important to consumers. There's no excuse for bad power management. Free software is available. It's easy to locate and fix these problems. And there's no reason why everyone doesn't do it. Better battery life is going to give your consumers a better experience and result in better reviews. So I've got time for one question, and then afterwards I'll be around to answer any other ones. Yes?
So you mentioned like turn off GPS or other camera when not using those sensors. But there are so many sensors on devices these days.
There are.
And most of them you cannot even turn off or turn on. You can like listen to them, but there is no way to turn them off. They seem like they're always on. Like why do they make it like that?
Well, one thing you can do is, you saw that when my app was idle, apps were still doing GPS fixes and things like that. You know, if the processor's asleep, you do have the ability to, you should avoid doing things like that. Also, if you're not connected, you know whether it's charging or not. So again, if the device isn't charging, maybe you don't do as many GPS fixes. Maybe you're not doing as much data collection. Maybe the intervals are spaced out. There's a lot of things you can do that are going to lessen that. Sensors are one thing the mobile devices do pretty well. Even though I have this set so it's listening 24/7, I still get better battery life. I'm in the 86th percentile, so only 14% of all phones get better battery life than me, even though I have some ridiculous settings. So the devices are getting much better at doing things like always listening and step tracking and all that. So I wouldn't worry so much about the device, but obviously you don't want to do anything to make the problem worse. I think we're going to switch over now to the next presenter, Kevin Sapp. And while they're switching computers, if anyone wants to take a quick bathroom break, come right back and then we'll be ready to go. Thank you very much.
Okay, everybody. Let's try to get started now for the next section. Thank you, Rick, for the introductions and for kicking it off. My name is Kevin Sapp. I also work at Qualcomm. I work on the Snapdragon Performance Visualizer. And it is a suite of tools that combined with Trepn, or kind of after you've used Trepn, allows you to really dig into what the CPU is doing, and also see, in some cases, what the DSP and what the GPU is doing. Take a lot of that information and put it all together. So, what is it? You know, everybody can read here. It's a comprehensive suite of tools, enable Android developers. We do support Tizen also, and most other Linux variants, for that matter. Okay. So one of the things, format session, just like Rick's session, interactive. So let's be interactive. Please ask questions. I'm going to ask questions of you. So let's kind of make it fair if we can. And my session will be introduce you to something the tool suite does, and then we will go into a demonstration of that. So I will try to keep the flip-flopping here between the presentation and the display of the demo as fluid as possible. Okay, so how does the Snapdragon Performance Visualizer work? So our tool is a little unique in that it is web-based. We have a small web server running on the target. You install the web server onto the target, as well as a whole bunch of other software that we create for you that understands both Snapdragon cores as well as ARM in general cores. The web server is the component that sits on the device. Technical people out there, anybody understand what a change root is? I warned you I was going to ask questions. So change root, anyone? So change root gives you the ability to run your own little system within the system. So we have our own little system within the Android system or Tizen system or OpenWRT, et cetera. It allows us to be very compatible with just about anything out in the market. And since we are web-based, that means that our GUI is a web browser. So our GUI runs on pretty much anything. I see a ton of Apple devices out there. So it runs on Apples, it runs on Windows, it runs on Linux. We prefer Chrome. Internet Explorer, we work on it as well. Firefox, Internet Explorer for some of our scalable vector graphics has some difficulties and challenges. For people who are a little more advanced, we support a command line. So you can SSH, secure shell, into the device, and we provide raw perf commands, strace, Perl scripting. If you're a script meister and you like to do that stuff, then we provide that. I see a question. I'm going to get a drink.
Just curious, when you said you run a server inside the Android,
Web
is that
server, yes.
in an app, and is it, what kind of server is it? Is it a Jetty server or what
it's
kind?
It's Mongoose, or since Mongoose has migrated to viral GPL, then we now use Civet Web, which is an offtake of Mongoose. Okay. We also have an automation. Oh, there's another question. I'm sorry.
Since your tool is web-based, are we forced to be on? Do we need a constant internet connection just to use your tools?
Pardon me?
Since your tool is web-based, do we need a constant internet connection to use your tool?
No, we do not. That's a very good question. I am using a connection right now. We use Dojo and JavaScript Dojo is a Google API for web, basically. We do provide a mechanism to allow you to download Dojo onto the device, and that way you don't need a connection. Very good question. And we also support an automation API, so that you can remotely run tests on it if you use any type of unit test framework or automation frameworks for nightly tests. You can integrate this into your nightly tests. Okay. So what can the tool do? I told you about how it works. We monitor performance. We look at the performance monitors, the CPU-based performance monitors, cache hits, misses, TLBs, hits and misses. TLBs, people understand, is the level, translation look-aside buffers, performance impact, cache hits, misses. We look at the L2 subsystem, which is more than just the cache. We can also have visualize system traces. So we take ftrace and put it into a nice GUI for you and combine that with a bunch of information. We also bring in thermal data, similar to what Trepn was showing you. We have, as Rick was mentioning, the Qualcomm Embedded Power Monitor tool that the team that writes the Snapdragon Performance Visualizer also writes that tool. They were designed to work and collaborate together. And you'll see how seamlessly they integrate a little bit later on in the demonstrations. We have memory leak detection tools as part of this. We also have kernel probes. Is that a question? And while he's bringing the mic, I'll keep talking. And begin and end markers, we allow you to put those in from Android and visualize those. And as you can see, it runs on most everything.
So you mentioned you monitoring the GPU counters.
Yes.
Are you now monitoring in the OpenCL mode as well?
For OpenCL, we're able to look at some of the issues as far as IB issues, and I can show you how those are. I don't have an OpenCL example. The performance counters primarily work for GL. Okay, so the tool has both live, real-time, or post-processed modes, which allows you to kind of see things as they happen or take a look at things a little bit later. Some pieces of data just happen too rapidly. You can't see them in real time. And for example, context switching. The cores come in and out so fast generally, you can't see that. And if you can see it, you're not seeing truly what's happening all the time. So we show you that in a post-processed mode. But we also support a real-time mode that shows you what's happening right away, because that's sometimes nice. In real time, we can show you the performance monitors, utilization, frequency, temperature, various GPU performance counters, DSP performance counters, etc. Okay, and our live view is what we call our bridge to our profile view. And profile view is the post-processing mode. The things that you collect during the live view session will display in our profile view session, or the static or post-processing session. Okay, so let's get to the first demonstration. So this is our home screen, if you will. And everybody like this? I heard chuckling. What's funny? Oh, you like the picture? Yeah, it's viewing into things, magnifying glass, looking into a view. So we try to make this friendly, very menu-like. And we talked about live view. So live view, profiling, there's live view. But dashboard views, we can see a simple overview if you'd like to see that. Some people go to this very quickly. This system that I'm talking to right now is called Boulder Fist. This is in Raleigh, North Carolina. So I have no devices connected to my machine. So web-based is really, really nice.
I have a question.
Oh, thank you. Better? This is going to be challenging. Okay. Sorry, guys. I think we need to bring it back over here. Okay. So other tools that we have, like I had mentioned, are live view. People are familiar with OProfile at all? Hands? Okay, couple, good. I'll talk a little bit about that. Dynamic print K, that's the probes that we had mentioned. It allows you to insert probes into the kernel code and not have to recompile and then see those marked in your system. We can take a look at the CPU frequency and its impact across all the nodes. And each bar on the right side represents how much time you're in each frequency. And you can hover over them and see. It's a nice overview. This system right here is running PowerLift Adreno test for 5 seconds and then doing nothing for 5 seconds. We have some logcat. You can pull a logcat out as well. Other utilities, Eugene was mentioning about frequency scaling. You can turn it on or off here. We provide a nice GUI for it. Okay. Brief overview. Live view. This is how we take a look at whatever you really want to look at. So I had mentioned DSP information. We have DSP here. Here's some of the DSP things that we can take a look at. We can toss a couple in there. Core P cycles. DSP is not doing anything. So select what you want. Various cache utilization. We try to group these so that they're meaningful. System overview and temperature. Once you have what you like, you select apply and then start. It looks like there's only one on here, so we can turn them all off and then just bring one on or another on. Stop. And if you want to zoom in and out, you can. You can zoom to the entire period of the last run by clicking that. Let's bring in the GPU busy. So as I mentioned, I was running something, Adreno test for 5 seconds, and you can see about 5 seconds in between here and here. You click to zoom. Here are your thermals. Well, I shouldn't see too much on these. Let's get that guy off. So we can see all the thermals here if we want. Okay. We try to provide a nice set of defaults here for people to use. And if those aren't good enough, there's something else that you'd like to add. We have configuration, and you go under live view configuration, and this shows you more. So here we have the category. So a whole bunch of different categories. Here's your DSPs, your ARM v7 performance counters, and then different sets of the performance counters. Barriers, if you're interested in how many barriers that you've happened. Very, very low processor details to allow you to see what is consuming the time. Here's the GPU pieces. Stall statistics, I can dig into these as well. Some of the L2 subsystem is available. And we also have the ability to set up custom information. Let me collapse this and show you something else here too. We also have strace. You can set in strace here and look and run an strace. So if you are missing something, you can set it up in here. Okay, let me go back to the presentation and we'll talk about customized data. Any questions? Okay, custom data. So we know that as part of the process that not always are we going to be able to figure out what everybody wants to put into these systems. And sometimes there's unique data to your application that you'll want to toss in and monitor with the other pieces of information that are currently available. And we provide the ability for you to put in custom data through various mechanisms. So first mechanism is what we call a file line field. People familiar with proc, sys, debug fs out there? So there's a lot of information in those areas that you can grab and plot them. For example, the run queue length or the run queue depth. And our tool currently doesn't have a run queue depth option for you to take a look at, but we're going to add one so you can see it. Another thing that you can do is you can use named pipes. So we support the concept of a Unix or Linux named pipe. You toss comma-separated values into that, and it'll be plotted for you using live view and then later for the profile view or the post-processing mode. Okay. Pretty simple. Here's an example of the code for you to toss in. Open the file or a pipe. We create the node, the named pipe node for you. And then this is going to print out a sine wave. And make sure that you flush, or if you want to set your file parameters properly for line buffering, you set your file parameters for line buffering, and then it takes care of it automatically. The other option is the file line field. And you can put in what file node that you'd like to take a look at, what line number, how far down you want to go, and then how far over you want to go. And it'll pull that automatically or periodically and toss it into the file. Okay, so I have an example of that. Let's go back to this mode. The other thing nice here about the web browser is we can have multiple tabs. Open all the time. So we have one tab for the configuration and another one for the live view. I have these set up. And sine test, I have the run queue average here, the sine pipe, and I'm going to kick it off automatically also. So if we just select those here and say apply, let's go take a look at how I configure those. Over here you see I have this sine test area. If we open him up, and we set up sine pipe, name pipe. So in here we select the system events filters, which is down near the bottom. Here. And the type we want is named pipe. Here. Sine pipe. And then we say, where do we want the pipe? I toss the pipe in temp. Yes?
Hi. I have a question. So the SPB is only for OEMs or the MTP? So I cannot download this
The
open?
Snapdragon Performance Visualizer is available on MDPs from Intrinsic, so you can get it there.
I can get the tablet and then download the software?
It'll be pre-installed.
Ah, okay.
Yes.
And are you planning in the future to open these for whatever tablet?
We have plans to get it out to more people, probably using a similar model with other devices,
Okay,
maybe less expensive devices.
thank you.
You're welcome. As you can see, we set up a pipe here. I called it S-Pipe 2. It's going to take double data, and the input I said isn't periodic. So let's close this out. Go back to live view. Oh, sorry. I need to talk about file line field. Like I mentioned, we don't have a run queue average in the system, so I created one. And we use system event filters and file line field and called it run queue average. And in here, we have a different set of parameters. Okay. And here's the file name. It's off in the sys file system. And then run queue stats, run queue average, and line number 1, field number 1. And once we start this, there'll be a little bit of a delay, and you'll see the run queue average being plotted, and then you also see the sine wave kick off. So there's the run queue, and there's the sine wave coming in after it. So you'll notice over here, too, that we have indication of when the sine wave was started. And also the mins max averages over here. If you want to zoom in on this area, you can zoom in here too. Okay, any questions on custom data? We feel that it allows you to add whatever pieces of information that you'd like into your applications and view them easily. Let's get back to the presentation. Okay, profiling and tracing. So the profiling and tracing combines the ability for statistical profiling. Everybody or anybody know what statistical profiling is, or profile? Okay, statistical profiling, what it does is it collects a bunch of samples and then takes those samples and allows you to see what's happening and where it's happening in your code. We do support directly the O-profile tools. We support perf on the command line. We also support additional visualizations that allow you to see at a very fine grain where things are happening within your system. Okay, so as I mentioned, profiling and statistical is sample-based. So in this example, is there a question? Okay. Every millisecond, for the examples that I'm going to show here, we wake up and say what's running and where are you running. We try to do a backtrace and figure that out. And if you collect for a period of time, it gives you an idea of where you're spending the most amount of time. Now, what some people don't realize is that you can also use some of the other performance monitors, such as cache hits, to instead of seeing where you're spending your time, to give you a better idea of where the majority of your cache hits or cache misses are. You can do the same thing with TLBs or anything that's available in the performance counters. This type of collection in general isn't real time, so this gets into our post-processing modes of collection. Okay. We also have multiple visualization mechanisms for it. We have a standard O profile for people that are interested in just a text-based output. We have that on a GUI that prints out the text. You can also use our command line interface. If you'd like to use that and you're more familiar with command line, then that's always a good choice. And one of the other areas that we provide are libraries if you'd like to do a functional analysis of your performance. So for example, if you're interested in determining which functions are taking how many cache hits, how many cache misses, or any other performance counters, we supply libraries that allow you to instrument your code and then show you how many of each of these metrics are happening in your functions. It really allows you to dig into your function to figure out who is the problem. Tracing. We also support various tracing mechanisms. Tracing is, I think, most familiar with ftrace. Does anybody know what ftrace is? Are we familiar with ftrace or atrace? Ftrace is kernel instrumentation. It allows you to see when things are happening. There's a whole bunch of information in the kernel where they put tracing or tracers in that allow you to see when things are happening and exactly. We take all that information and put it all together in a plot. Some of the information that you can see are exactly when the frequencies are changing, exactly when one of the GPUs issued a command, exactly when the GPU frequency and the GPU power states are going up and down. And I'll give you an example of that in a minute here. I think it's next. Yes. Okay, let me move over to that. So as I mentioned, Live View is the gateway for the profiling or the post-processing analysis. How we get to it is we select channels, and here you can see profile view selection. So if we open it up, we have two types. We have CPU profiling, which is a very similar mechanism to O profile, but we take a time-based approach, and I'll show you the benefits of that here. And we also have a time chart, which is ftrace, shows you the GPU events. It shows you each process as they're being swapped in and out, what core they're running on. So let me pull out some of these and bring in. Let me bring in this phase. And we'll bring in the system overview as well. And we have those. Let's press apply. And when we press start, you'll see some information and the typical plot that we showed you before. And down here in this area, you're going to see when an application is started and when it is stopped. And there'll be little round markers over here too. Those are really nice visual indications. So what we've done with this tool is it allows you to set up a test and say, when I hit the start button, start the test, start the collection, start my application, and then it also tells you when your application is finished. So let's give it a try. Okay. There's when the application started and when it stopped, so I know I don't have to collect any longer. And if we want to look at all the information here, we can take it some time and zoom in and out if we prefer. How you get to the post-processing is using the Analyze button right here. It's going to pop up a new window. And what's unique about this, it does take a little bit of time to generate. And this is going to Raleigh. What's unique is the data that we're putting together here is it's JavaScript, it's self-contained, it's also self-contained with the data. And we use scalable vector graphics on it. So you can take this file and download it and send it to a friend, and the friend can see it and manipulate it just like you can. There's no application that's necessary to look at it. Okay. So just a general overview here. We can see all the different cores when they're busy. We can see CPU 0 is busy all the time. We can see that 1 went in and out here a little bit. I had mentioned GPU information. Let me get rid of this hover here. So we can see something started happening right here, that the GPU kicked in. And as I mentioned, this target is running Adreno core, and it's running for 5 seconds and sleeping for 5 seconds. So the period between here and here should be about 5 seconds or so. So 4.7 seconds. These are what we call calipers. They allow you to change the viewport that you're looking. If you notice, these values change when the caliper moves. So, Surface Flinger application does the graphics. These green, bright green highlights, these are your IB issues. We can zoom in on those. The triangular ones are end of frame indications. So you can see when an end of frame comes in on your GPU. You can see your power states. Let's bring up the legend here. Sorry, I should have done that earlier. So here are the GPU issues. Someone mentioned about CL. CLs would be in purple. Other thing that we can do here for the GL issues is you can look at your frame rate right here within that area. Our frame rate is 162 FPS on this device. We can bring in any process if we're interested in seeing, here's the Adreno test. We can spread him out. Now we can see which cores he's running on. He was running on core 1 and core 2 primarily. Oh, sorry, 0 and 1. This chart down here is our CPU profiling. This is the sampling. Let me show you here. For its options, I had mentioned I started an application. So we can do a functional analysis here. If we click on it, we can see full backtrace. These are all kernel functions. So who called, where it came from. And if you have the source code or you've compiled for debug, you can get even more information. Sorry, bad mouse. Okay. We can filter as well. If you're only interested in a certain application, you can take everything out. except one application that you might be interested in. So if we're only interested in, well, we'll say the Arduino test, we can see where he was running. And if you have libraries debuggable in there and compiled, you can click in there and see. We can also perform a hotspot analysis. And this shows you where in your code you're running into problems. Okay. Any questions on that? It's actually quite powerful if you understand it. Really, any questions? Yes.
The code part you just showed, that's assembly, right? So is there a way to get a little bit higher level?
This portion?
Yeah.
Were you asking for C?
Well, I mean, like for your application code, if you're narrowed down for example, you see some parts of your application is performing slow,
yes,
and being able to narrow down to the line of code in your application, not some low-level function calls, right? Is it possible?
Yes.
Okay.
So I can see if I have an example here. I believe it's the same one, actually. So let's just bring in. We'll run the same test, and without quite as much of the other information in there. Start. Press analyze. And what we'll be able to show is, it'll still show the assembly language, but it's going to show you the lines above it. A lot of times your performance comes down to, on the complex processors, your pipeline, if you've put the instructions in the correct order, if you have a memory access that's delayed, you can sometimes insert other work in before that if you need to. So let's, profiling options, functions. Let's see if we can find where it is here. Okay. So here's my application. And you can see here the line numbers where you're at. And the line of code. Oops. Is that what you were looking for? Okay. Sorry. Bad mouse. This gives you a nice histogram, too, of where all your hits are. Okay, let me jump into the power. And we have a sister tool that Rick had mentioned before, Qualcomm Embedded Power Monitor, that we are able to collect the data on and correlate with all of this information as well. So we look at the power rails on this. We have a sample rate of up to 50,000 samples a second. We can correlate data with temperature, with all the other information that we just showed you on there. It's also web-based and put together by the same team, so they work really, really well together. Okay. And I'll just jump into a quick demonstration of that.
Quick question.
Yes.
You said that it monitors the power rails.
Yes.
So do we would need a reference device to actually have the measurements of the rails? Because Rick mentioned previously that you can only measure rails on non-production devices.
Yes. So there are a couple of options. And it depends on who you are, who you work for, and those kinds of things, and how much time you have. We have devices that have the EPM circuitry on them, and they are available to some of the larger OEMs. And one of the other areas that we do is we have a bill of materials that allows people to modify their hardware to be able to monitor the power. We provide that for free, and some of the engineers will even help you with the hardware modifications needed to do the power collection. The other option, time, is we are working on adding the EPM support to provide this level of fine-grained power collection to the MDPs, and that's going to be available sometime next year. Okay, so I'd mentioned that the tools are written by the same team. It is a different port, and this port happens to be running on a Linux box and uses the same technology. The way that this is set up is the collection is done through a SPM card or an external card. We can monitor the board power coming up. And this is used internally at Qualcomm during our bring up as well. You don't have to have any software whatsoever running on this device in order to monitor power. It happens that this one is running Android. This is the same machine that I've been connected to and been demonstrating. So we'll be able to show the power changing with the Adreno test that was running. You'll see for 5 seconds the power rail for the application processor go high and then come back low again. So the tool is live view, again, same tool. And let's select the apps processor. Name of the core is crate. Let's select the current. And just one rail for now, and start. You'll see in a few seconds it'll drop. Okay, so now let's go back over here to live view, and let's say channels. And if we go to the bottom here, there's this button called Sources. Let's click it. Let's type in and if you notice, this is the same address I typed in before. If we add that, press apply. So now we have these channels for the power brought into our Snapdragon Performance Visualizer that we can control them. So let's go back here to this apps. And where was it? There it is. Let's select that. Go back down. Let's get rid of that. Let's just do time chart version. And bring in the thermals, apply, start. Let this run for a few seconds so that we can get an up and down cycle of the GPU. And if we want to, we can take a look at the GPU busy here. There's the power, and there's the GPU. And see how they're correlated here in the live view. Let's look at the analysis. And this will show us all the rails. This will show us the GPU utilization. This will show us the power states. This will show the GPU IB issues going in with a whole bunch of detail. The power channel is in a different color here. And if we want to move him up to closer to the 3D utilization, we could make them bigger. Let's just bring in the GPU information. You can see here where the GPU and the power went high. And we also have more activity. Here's where all the IB issues or all the activity on the GPU is happening. And we can zoom in and look at these as well. And we can break apart, again, to see which cores they are running on. We can see the impact of the power state on the GPU, you know, how much time it was in each power state. And this gives you a very fine-grained set of information for all of your processes, for all of your threads. It shows you your various wait states, as well as it allows you to add all of your custom data to bring into the application, so you can make this tool whatever you would like it to be. Okay. Any questions on that? I believe that's it. I'm finished. If there are any more questions. Okay, next let's take a couple-minute break, and then we will be back with is it Dave, are you giving it, or Manish is giving information about Adreno Profiler, some very, very cool stuff, so please stick around. Thank you very much.
I'm getting a lot of questions about slides, and I've just confirmed that Samsung is going to take the slides, the same slides we presented today, and they're going to make them available after the conference. So I guess everyone will get an email and they'll get a link where they can download them. So just wanted to let everyone know.
And just a reminder, we will have our engineering teams, after Manish is done with Adreno Profiler, we will have devices for you. So if you want to profile an app, ask questions of the engineering team and go through some of that testing, they'll be on hand to do that.
Hello? Perfect. All right, guys. So we're going to start with the next session. We're going to talk about graphics and gamings. So just show of hands, you know, how many of you guys consider yourself a game developer of some sort? A handful. That's good. So, I mean, you guys saw a lot of cool tools. What we're going to switch to is a more specific use case, which is graphics and gaming. As you know, gaming is the most popular category of applications on Play Store or mobile today. Gaming, we expect $22 billion in revenue for 2015 for mobile gaming, which is more than PC gaming. So this is the first time the mobile gaming is going to surpass in terms of revenue to PC gaming. And to put things into perspective, it is also comparable to the whole McDonald's restaurant chain revenue. So you can see, you know, how fast and how big it is already. Overall, you know, gaming is also a very unique use case in a way that it stresses multiple parts of components of chip or system on chip, and it does require and deserve specific tools. So we're going to talk about gaming-related tools that we have. But before I dive into that, I would also like to give you an insight of how the hardware is and a little high-level overview of how the SoC is for gaming before we dive into it, dive into the tools section of it. So let's focus on the quality of graphics first. You know, mobile has reached a point where the quality of graphics is very similar or very comparable to PC today. And if you can focus on this slide and imagine, I mean, I've noted out which one is PC and which one is mobile, but if you can try to identify the differences, there are very minimal or none And this slide is actually coming from Epic's Unreal Engine 4. They presented this at GDC as well, and they rendering it out Snapdragon 805 on the right-hand side, which is the same processor that is in Galaxy Note 4, and then the PC on the left side. So when someone like Unreal Engine maker Epic is saying that, you know, we actually are getting same rendering quality as a PC on mobile, you know, you got to believe it. The next thing that I want to point out is relative performance, and this is just your graphics or gaming performance. And this is based on number of graphics benchmarks that we ran on multiple devices and compared them. So on the left extreme side where you see 1, that's the Nexus 1 device that was launched in 2010. And now we are 4 years down the line. Galaxy Note 4 launches with Snapdragon 805 processor, and it's 65 times graphics performance than what it was in the first Nexus 1 device. So in 4 years, we've done a quite significant amount of journey already in terms of graphics performance. So just put that number in mind for a little bit. Next thing what I want to do is I want to represent a scene from a popular game from Gameloft, Modern Combat 4, and then kind of focus on visual elements of the game, and then help you guys understand how those elements are processed on the hardware or the processor. So as you can see, there's a lot of things going on within this scene. Of course, there's AI or artificial intelligence, which is basically, for example, here the chopper is moving. You know, you gotta have that movement, how that enemy chopper moves in. That needs to be controlled by some sort of code or functions, and that would be your AI. There's of course physics. When something explodes, you have lots of particle effects. How do these particles behave? That code has to be written. There's animation, so you see that boat. You know, when the water is moving, you know, there has to be a movement of the boat as well to match it, so the scene looks a little more realistic, and that has to be calculated and animated somewhere. There's of course lots of graphics elements. You see the blooms, you see the explosions, and the particle rendering. You know, all that and the high-res textures, of course. So all that has to be processed and controlled somewhere. There's also surround sound or audio that goes along with the game, which makes it more immersive experience, and that has to be processed as well. And of course, if you're playing a multiplayer game, you know, you need a connectivity. So there's lots going on within this. I mean, when you play a game, you don't realize, but there's lots of other different components within the SoC that are talking and operating to deliver the experience that you want within the game. So one step down, you always see it from the application developer standpoint. I do want to give you guys a sight of how it is from the processor standpoint, how these different elements are processed. So the first, where you start, of course, CPU. You know, you have your AIs and game logics and all these code running on CPU. You have multi-core CPUs. You have different functions spread across multiple cores of the CPU, however you want, but the CPU is where you start. Now, when you process all these animations and physics and AI on CPU side, you pass on only the command pointers to the GPU. Now, GPU is the main heart of the game processing, because all the pixels that you see, all the colors that you see, are actually the translation of the triangles and texture data into the pixel visual data that gets displayed onto your LCD screen. And that's where the GPU comes in. Now, GPU actually goes in and fetches all these data from the system memory. System memory there's no video RAM like on PC. There's the same system memory that is shared between anything that is running in the background, Android operating system that is running in the background, as well as your application. So it is a single system of memory. Then GPU goes, fetches all that data, processes it, converts it into pixel data, and then puts it into a final frame buffer. And then final frame buffer, the display engine basically takes that up and then portrays or displays it onto a display panel, which is LCD. So all that processing, of course, you require an audio, of course, and video elements if you have like a cut scene going from one scene to the other. all that does require multiple components of a processor, and they need to be operating simultaneously and cohesively in the most efficient manner to give you the best gaming experience. And Snapdragon and Qualcomm, what we do is we actually have, we own all these different elements. We have individual teams working together on this single processor, so we do deliver the best gaming experience here. Now let's focus on Galaxy Note 4 as an hardware for this gaming use case. So as a processor, it has Snapdragon 805, it has CPU, quad core up to 2.7 gigahertz per core. The GPU is Adreno 420 GPU, and I'll go into GPU details a little bit more. It has a DSP to process audio and some of the other things that Rick was mentioning before. Display, it is capable of doing 4K Ultra HD displays, the processor itself, but the LCD on the Note 4 is 2560 by 1600. And we also have, there's a huge increase in the memory bandwidth. We almost get like 25.6 gigabytes per second. That's even greater than what you get on Xbox 360. So that's huge. And in overall specs, you know, GPU, CPU, memory, you're very comparable with the consoles. So let's focus a little bit more on GPU, because GPU is an important part of the games. So in Samsung Galaxy Note 4, the GPU, as I said, is Adreno 420 GPU, so the newest generation of GPUs on Adreno GPUs that we make internally within Qualcomm. But it does have the highest level of specification that any PC or console has today. So it does have features like tessellation, geometry shaders, all those supported on Adreno 420 GPU. So on the left side, you have a non-tessellated Hornet image, and on the right side you have a tessellation enabled on the same Hornet image. And you can see the difference. There are more details on the back of the Hornet, there are more details on the ground. You know, all these are basically additional triangles that were generated by the GPU, and then you use with the techniques something like displacement mapping to add more effects into it. So now as a game developer, you are not baking all these effects into an art asset. These are generated by GPU live and dynamically as the game is running. So which is a very high-end feature that is used in, you know, PC games like Crysis and Far Cry and some of the other high-end games. Now it is possible on mobile with on Galaxy Note 4. So in terms of APIs, how these features are available, you guys are familiar with OpenGLES 1, OpenGLES 2. Yes, we support that. We also support OpenGLES 3, which was announced last year by Kronos. OpenGLES 3.1 adds up lots of other functionality, including something like compute shaders, so we support that, and also Android Extension Pack, which adds up geometry shaders, tessellation, and other features. So we also support all that on Adreno 4X GPUs, which is part of the Galaxy Note 4. Some of the GPU architecture highlights, and these are important because when Dave starts getting into the optimization guidelines, you can relate all these back to what I'm saying just over here. So Adreno 420 GPU within the Galaxy Note 4 is tile rendering architecture GPU. So what that means is instead of processing the complete frame of the game, we process it in batches or tiles. So on the left side, if you see that whole frame and how it is divided up into small tiles, each individual tile is then processed within the GPU local memory, and all the effects like your transparency, alpha blending, all that are happening locally in the GPU, and then final pixels, when they are ready to just written out, then they go out to the system memory as a final frame buffer. So it's an efficient way of processing complex scenes. It's getting more and more common with other GPU architectures, but this is something that Galaxy Note 4 GPU does as well. So essentially, you know, if you're using transparency or blending, those kind of effects are less expensive in terms of performance. We also have what we call as early Z reject feature. So if you're drawing a scene, this is important for you guys. When you're drawing a scene in a game, you always have to draw front to back. So front to back is basically in this particular scene, you're drawing a spaceship first, then the rocks, then the planet, and the skybox. If you draw it in those order, you know, some of the pixels that are for skybox, for example, that are behind this planet or rocks that are not visible, you give GPU a chance to completely eliminate processing those pixels. And that's some of the advantage that even PC and consoles have today, and we support the same feature as well. So it's very important to remember to draw always from front to back. Always draw the object first that is closer to the scene, closer to the camera. The other couple of features that I would like to highlight, one is the Dynamics Flex Render technology that is unique to Adreno GPUs. It is basically traditional desktop style GPU rendering as well as the tile rendering architecture that I just explained, supported both dynamically within the frame. So for example, if your scene is very simple enough, you know, just split operation, you can render it through the direct rendering architecture. If your scene is very complicated, a lot of alpha transparency, you can render it through tile rendering architecture. So, and as a developer, the cool thing is you don't have to worry too much about which rendering mode I'm in. A GPU and the driver mode decisions are made based on the scene complexity. We decide which is the best mode of rendering, and we switch to it accordingly. And this you will directly translate into, you know, power savings or performance improvements that you may or may not generally know, but this is just good note for you guys to make. The last thing is the shader double rate half precision design. Basically, we do respect the precision of the shaders that you specify in your pixel or fragment shaders. So for example, most of the GPUs today on mobile, it doesn't matter if you have a high precision or medium precision specified, or medium P or high P for that matter. And it always processes at the same speed. But on Adreno GPUs, if you're using medium P, which is mostly the case on all the games, you are going to get twice the performance. So basically, our architecture for the shader pipeline is scalar. So we do support twice the performance for medium P shaders. So always use medium P shaders. Only use high P when you only need it. But you can even mix those up, like some of these variables could be high P and some of those could be medium P, and we do have all those samples in the Adreno SDK too. So with that, a high-level overview of architecture and hardware, I do want to pass on to Dave Astle, who's my colleague here, and he will go into a little bit of optimizations, and then we'll come back I'll come back and talk a little bit more about the tools before the demos of the tools. So Dave.
All right, thanks. So a lot of this will touch on some of the things Manish talked about in regards to our architecture. So the first optimization, the first best practice to pay attention to is how you're using FBOs. So this is an example of the worst case pattern for FBO usage. So as your frame progresses, you initially start rendering to the frame buffer. You then switch to your first FBO, draw to that. What happens when you do that is that because you're going to need the data in the frame buffer to render later, we have to store that out to main memory from the tiled memory. And then when you draw the FBO, we have to load the data back in from the previous usage of that FBO. When you're done drawing the FBO, then we store that information out, switch back to the frame buffer, and draw again. So we need to retrieve the previous data from system memory. And then at the end, we write all that out to system memory. So there's a bunch of additional copies between system and GPU memory that happen when you do this that are problematic from a performance perspective. So the correct way to do this is to start off by rendering your FBOs. And the first thing you want to do is invalidate frame buffer. What that does is tell the driver that whatever was in the FBO previously you don't care about. Now, of course, if you do care, then you can't use this, but typically you don't care what was in there previously. So you tell the driver that it doesn't need to load the previous contents into the FBO, so you avoid that load. And then when you're done rendering to the FBO, then you switch to all of your FBOs, then you switch to your main frame buffer. You clear it, again, to tell the driver that you don't need the previous contents of the frame buffer, so it doesn't have to load that, and then draw. So in this case, what happens is you have the one store when it's done rendering the FBO, and it stores again to system memory when you're done rendering the frame buffer. So you avoid all those additional loads from system memory that can be very expensive. So just in general, for any number of frame buffer objects you have, just invalidate them initially, then draw them, iterate through all of your FBOs, and then switch to system memory, or to your frame buffer, clear it, and then do all of your drawing. So similarly, we have the same kind of issues with dynamic vertex buffer objects, where you update the VBO, you draw, you update the same VBO again, you draw, update, draw. In the worst case, what happens because of our binning architecture is that we have to end up keeping multiple copies of your data around, which can, again, hurt performance. And that happens even if you're using buffer subdata. Yeah, so in this case, what ends up happening is for each bin, we keep copies of that data around. So the optimized way to do this is if there's a single VBO, just update that all up front and then do all the drawing using it. If you're using multiple VBOs, again, just update them all prior to starting to use them. So Manish mentioned that we do early Z rejection. So knowing that and taking advantage of that in your rendering engine can help improve performance significantly. So the first thing we recommend is that you sort by material. So that reduces expensive state changes between shaders and texture states. To sort all of your opaque draw calls front to back. This reduces overdraw, so you're not shading pixels that aren't seen anyway. And because we have early Z rejection, it actually works quite fast. As the note says here, in some content we've seen that it's fragment bound. We can see as much as 10 millisecond per frame in performance from doing this. And then related to this, just drawing the skybox last, since typically a lot of your skybox isn't visible anyway. If you render it last, like it's only drawing the pixels which are actually visible. So an optimization on shader performance. We do 16-bit floating point operations twice as fast as 32-bit. So we recommend that by default you use medium P precision in your shaders. There's some cases where this might not work. Depending on the content, it might not be enough precision, but we suggest you start off with this and then only increase the values that you need to high precision. Also, Adreno is a scalar architecture since Adreno 300. So it used to be that, with vector-based architectures, you'd want to try to pack as much information into a vector as possible so you're not wasting silicon when doing arithmetic on that. With the scalar-based architecture, that's not necessary. The important thing, though, is that you don't use components you don't need. So if you really only need RGB and aren't using the alpha channel, or you're not using the W component, just declare your data as vec3s and don't waste that extra slot. So if you've worked in the console or PC space, you're probably familiar with tessellation. So tessellation gives you the ability to substantially reduce your memory bandwidth and CPU cycles by sending smaller data than will actually be rendered. So additional data, additional geometry gets created as part of the tessellation stage. So it adds a bunch of visual detail and quality without requiring huge models and huge processing to be involved with that. So what's important, though, is to make sure that you're doing this intelligently. So a potential problem is if your tessellation ultimately ends up creating sub-pixel triangles, that could actually hurt performance. So you want to make sure that you're taking into account the distance of the geometry you're rendering and things like that, and do a smart adaptive tessellation. In the graphics pipeline, backface culling occurs after the tessellation stage. So it's potentially possible that you create all this additional geometry which just gets rejected because it's backfacing. So there's ways to deal with this within your tessellation shader itself. You can identify whether or not that primitive will end up backfacing, and then you can just set their edge tessellation factors to 0, and that will save having to process that. You may have to fudge it a little bit if you're using displacement mapping, because it could change the visibility of the primitives a bit. And then whenever possible, you want to disable the tessellation stages of rendering if the tessellation factor would be 1 anyway. It causes it so that we don't have to use those portions of the GPU. And that's it. If there's no more questions on that part, we'll go back to tools.
Do you want to? We can either take questions on that. Feel free to ask questions. Or we have tools section that we can cover right now. Let's just proceed with it. If you guys have questions, please feel free to stop us. So tools, of course, if you're a graphics or game developer, the whole tool chain, but you basically are creating some sort of assets in some sort of tools like 3D Studio Max or Maya. You have lots of textures that you're creating through something like Photoshop. Then you're trying to compress those, write a code, then emulate the code on a PC, compile it for the device, deploy it onto the device. Then you're trying to profile or analyze the code while it's running onto the device. And then once you're fine with the performance and power, then you're deploying it onto your Play Store, right? So that's usually the process. We also understand that a lot of you guys are also switching to middleware like Unity and Unreal, and that is also an important factor for us. So we do work closely with Unity and Unreal, and most of the optimizations that you just saw in the previous slides, we actually made sure those optimizations are included in Unity and Unreal. So you'll get those out of the box. But for the rest of the, I mean, if you are hand coding all throughout the pipeline, we have tools that go into each of these individual stages and help you optimize. And basically, the way we package these tools and provide it to you, there are two categories. One is Arduino SDK, and the other is Arduino Profiler. Arduino SDK is basically a collection of utilities, you know, lots of samples, documentation, libraries, and all that about OpenGLES, OpenCL, and other APIs that we support that are available as part of Arduino SDK. And Arduino Profiler is a runtime analysis tool. It's supported on Windows, Mac, and OS X and Linux, and enables detailed analysis of the GPU, CPU, and some memory level utilization. And it is basically works on the commercial device and works with commercial apps, so you don't have to root the device or flash any new build to get it working, which is the ideal case scenario for people like you anyway. So Arduino SDK, as I said, you know, it has collection of huge samples. These are just some of the examples, but if you want to, let's say, play around with shaders, you know, create a fur effect or hair effect or a realistic metal or skin or plastic, you know, all those sort of effects, we have all those samples available in the SDK that you guys can download. We do also have texture tools, so if you want to compress in different texture compression formats like ETC, ETC1, ETC2, ASTC, ATC, you know, all these different texture compression formats are available. We have a visually based tool that you can compress, as well as a library that you can plug in your tool chain to automatically compress your textures as you you make a new build for the games. We also have thorough documentation. So as I said, we have OpenGLES 1, 2, 3, OpenGLES 3.1, and Android extension pack documentation and best practices, how to write a simple triangle all the way to how to write a complex scene. We have all those samples and documentation as part of the Arduino SDK. The new thing that we've added as part of Arduino SDK, which I just basically thought I would mention because someone over here did mention about OpenCL. So we actually, in the latest release of Arduino SDK, we have OpenCL debugger that does work on Samsung Galaxy Note 4. So if you guys, or Note Edge, both devices that are based on Snapdragon. So you guys can actually start debugging your OpenCL kernels while they're running on your Samsung device. So that was like an overview of what is in the Arduino SDK. Arduino Profiler is a really cool tool, and I think, you know, to best do justice for that tool, I think you should see the demo. So Dave, we're going to switch to Dave, and he's going to show the Profiler demo.
Okay, so this is Arduino Profiler. I'm connected to Assassin's Creed Pirates, which has been kindly provided to us. First off, like Profiler is supported on any of our commercial devices. It's actually very closely integrated with our commercial drivers. So any commercial phone based on Qualcomm Snapdragon Adreno hardware, you should be able to use it with it. So initially when you start up, you'll connect and it will show any of the applications it detects that are using graphics, and you can choose which one you want and connect to that and then start profiling. So the first thing typically you do is open up a scrubber frame. So this is a scrubber GL frame. So this allows me to capture a single frame from the application. So I would start a capture and it will go and basically freeze the device and capture all of the information associated with current frame. frame. So that includes all of the API calls, all of the texture data, all the shader objects, and everything, and it sends that over, we do some processing on it, and then you can interact with it from here. So the first thing I want to draw your attention to is the comments. So we look through the API trace and we look for potentially problematic things and call those out here, so those can be some of the first things you start looking at for potential performance areas. And then over on the left here we have all the draw calls, so you can actually step through these and see the scene get rendered. This is using our desktop OpenJLS emulator. So you can step through these calls and see the scene as it's being drawn. So I'm going to jump down here to, they're doing off-screen renderings. I think this is the final call into the main FBO before they do the overlays. And then from here, so this is showing all the draw calls. In addition to the draw calls, I can see any other OpenJLS API calls that happen between the current draw call and the previous one. I can see the OpenJLS context of the current frame or the current draw call. This is stats for the entire frame, so I can see, for instance, like how many calls there were in total, like how many redundant calls, and all this kind of information. I can see the data for the VBOs and the index buffers, as well as element data for the current draw call. Something that is shown up here that this application does demonstrate, there's an extension added called EGL debug marker. So this allows you to mark your geometry in your draw call. So as you're rendering, you can basically set hierarchical markers. So say you're drawing like all the characters in your game, you can indicate you're drawing your characters, and then for each individual character, you can push and pop those names onto the stack. So that when you profile it, then you can actually see which draw calls are associated with which objects in your game. So you can really closely correlate that information. So you do have to modify your application in that case to take advantage of that. This one hasn't, so I can't really demonstrate that, but it can be a very useful feature. Most of the stuff available in Profiler, you don't have to change your application at all. So let's see. You may have noticed this column here on the right, which is color code. So this is actually the number of clocks. So there's this metrics tab here at the top, so I can choose any of a number of metrics to include as part of my capture. So I had clocks when I did the initial capture. If I want to add additional things, I would have to capture again. So I can add that, and then when I recapture, that would show up. So I'm showing it graphically here, and if I select this, it'll actually color code the scene based on that. So I can see kind of where my hotspots are and see that, you know, the things that I expect to be expensive actually are. There's one game that we have that's a tennis game where when you do this, the only thing that shows up as red is the tennis ball, which is taking maybe a total of like 20 or 30 pixels on the scene, but they're using by far the highest number of clock cycles on that. So you could quickly be able to see things like that and make some quick optimizations using this feature. If you don't want to see the color, you can actually see the values as well, so you can see actually how many cycles numerically each of these calls is taking. Let's see, let me go back to this. So I'm currently viewing the color buffer. I can view the depth buffer as well. If the stencil is being used, which I don't think it is, or the alpha buffer, those can be viewed here as well. If you want to see the binning configuration, so this is basically how the screen is broken down into bins, you can select that. There are some optimizations you can do around this. They tend to be somewhat device specific, so it's not generally a great place to optimize, but if you are having a particular performance related to binning on a device, you can use this to say, like, make sure that one of your UI components isn't straddling bins or things like that. Turn that off. Get back to this call. Sure, go ahead.
Are these tools only available on Windows?
No, they're available on Windows, Mac, and Linux. Yeah, we released the Mac and Linux versions a year ago, so we support all three of them now. Yes?
By any chance are you going over VGA to the projector?
Yes, I am.
You jiggle the connections, it looks like it's as good as the VGA.
Yeah, I don't know if there's anything we can do about that.
I thought I saw it better before, but...
Yeah, it could be. I didn't have enough HDMI to display port adapters to get this set up in advance, but you can come look at it after. It does look a lot better, actually, on the display. Let's see, where was I? Oh, so in addition to regular mode, you can view the scene in wireframe if you want. We also provide several different overdraw visualization modes. So each pixel, the wider it is, the more that pixel is overdrawn. And there's different ways to visualize this, but you can really easily see maybe if there's too much overdraw in your scene and it's hurting your fragment performance from this view. So that's it for the main screen. In addition, I can view all the textures, so hopefully. So I can see all the textures that are being used. It'll show the resolution as well as the format. So most of these textures that I'm seeing in this are actually RGB8 and not compressed. So that's actually one optimization recommendation we make, is that you use a compressed texture format as much as possible. It saves on texture memory bandwidth, it saves on storage space. It can have some big performance gains. But you can view all the textures here. If you want to, let me see if I can find one that uses MIP maps. So you can actually replace MIP levels with solid colors. So if you have one that's being used in the current scene, you can really quickly see, oh, you have no reds showing up. So maybe I can use a lower resolution for my base MIP level and save on some memory bandwidth there. Revert back to that. You can save out the textures as well. And view all the programs that are being used. So and since I sampled clocks for the draw calls, I can also see here that this one is my most expensive shader as far as cycles go. I think it's actually the one that's shading the overlay, so I'm not seeing that with the selection. Yeah, so I can see some of these here. I was trying to find the boat, the one that's shading the boat. But so for each of these shaders, you can see what the most expensive are, and you can also see the source code to the vertex and fragment shaders down here. And for each of the shaders, we do run analysis on it. So this is actually using a compiler on the device to provide statistics on the shader overall. So this includes like the total number of instructions, full precision ALU instructions, half precision interp instructions. So you can see how expensive that particular shader is in each of these areas. And the way you would typically use this information is if you identified a shader as being too expensive, you could start making optimizations. And the cool thing about this is that you can actually make changes to the source code here and send it to the device and see what kind of an impact it has on performance on the device. So if you want to change, maybe you use like a lower quality shader, want to make sure that it still looks okay like that, but that it actually does improve performance, rather than making those changes and then rebuilding and redeploying your application. You can just instantly make those changes and see what they look like on a live device as you're using this. One limitation is that this is not a lot of screen real estate to be working in. So we do have this shader analyzer view, and you can just go over here and copy shaders, and it'll grab the current shaders that you're looking at and copy them over here, and you can edit them in this workspace. I don't know why these regions, the text regions, are clipped like they are. I'm using like a development version of the tool, and clearly I need to file a bug against that, but normally you would have all that screen real estate that you could use to edit your shaders. And as you edit them, assuming the shaders are valid, the stats at the bottom will update. So if you decide that you're using too many ALUs, you can edit your shader and actually make sure that the number of ALUs does decrease, and that our compiler wasn't like already figuring out the things that you did to optimize it. So back here, the only other thing I want to mention, if you're doing anything unusual with swapping, like typically at the end of the game, you're going to call EGL swap buffers at the end of a frame. And so we can identify what a frame is based on that. But maybe you're doing something clever with only like partially updating portions of the display, and you're not using swap buffers, using flush or finish or something else at the end of your frame. You can use this panel to actually change what we identify as a frame. So it's what we call our frame delimiters. So you can change it to whatever your application is actually using to make sure that we can actually capture. And then the other thing the other main mode of this is the grapher mode. So our GPUs have several hundred performance counters. We let you connect to a subset that we think are relevant to application developers and monitor them in real time as your application is running. So I've grabbed a bunch of them here. This includes the frame rate, the percent that the GPU is busy, the vertex fetch stalls, texture fetch stalls, GPU L1 cache misses, average size of your polygons, texture memory usage, overall memory reads. So I can monitor all these as the application is running. The full list of metrics is over here. For each one of these, if I select it, like we provide a tooltip describing what that metric means. In the cases that that we think that it should be within a certain range, we'll provide recommendations for what those should be. And then if you're not in that range, some things that you can do to try to get there. An interesting thing to do in conjunction with this is you can do these overrides. So this is what's over here on the left. You can override various things. So actually, let me go down here to the bottom. So force IFD, this forces the driver to act as if it's infinitely fast. So basically, none of the APIs actually do anything at this point. And when I do that, I can see that the frame rate jumped from like just under 25 to I maybe picked up like 3 or 4 frames. So this does tell me that I can get some performance improvement from doing GPU-centric optimizations, but that I may have CPU limitations as well, or what's limiting my performance. But I can do other experiments like this. So there's, for instance, for small textures. So if I think maybe texture memory bandwidth is my issue, I can do this and it will replace all my textures with 4x4 textures. In this case, I didn't really see much of a performance difference, so as far as the frame rate goes, so maybe that's not my issue. But if it was, then I could, for instance, use smaller textures or switch to using more compressed textures or something like that. But you can use this interface to do a bunch of experiments to like really try to identify where your bottlenecks are and then start to make changes to get to a performance level that you find acceptable. And this is actually monitoring the performance counters on a per process basis. So this is just looking at the application you're profiling. Of course, the GPU is being used by other things potentially in a given time. So we also have this global mode where you can grab a bunch of these metrics as well. So you can see, maybe like your GPU performance is hurt, but there's something else that's using it all the time, and that's really what the problem is. You can see from this view maybe more of what's going on. And I think that's everything for the profiler. Any questions before we move on to the SDK? So they potentially could indirectly. So they're overriding context settings other than, I think the IFD and IFH mode, those are global. Everything else is specific to your particular OpenGLES context. So they could, because they're affecting your application using part of the GPU, they will affect the aggregate somewhat, but it's only those two that will globally affect everything. Okay.
Okay, I think we can go to the SDK.
Okay. So as Manish mentioned, SDK is really kind of a container for a bunch of additional resources we offer to anybody developing for the GPU. So this is kind of the intro. We provide, as mentioned, over 100 different tutorials and samples. So there's some samples here. So I'll pick the NPR one. So this gives an overview of what the sample is. I can actually view the source code from here. So this shows me the directory structure where this stuff is, and I can actually open these, and I'll open it in whatever my code editor is. And I can view all the files associated with here. I can actually run this from here. So this will launch the application on Windows using our desktop emulator. If I want to, I don't have Android dev tools on here, but I can also use these buttons to build it for Android and then like install it to Android and run it on a device. So all of our samples are set up to build for Android by default. So you can look at all the source code there. Like in general, we follow best practices with our samples. So if there's something you're trying to do that you've maybe never done before, or like want to see if there's anything special about the best way to do it on Arduino, you can look at these samples for these techniques and figure that out. We also provide other tools here. So one of them is the Arduino texture tool. I mentioned earlier that compressed textures are important. So this tool lets you like set up a workspace where you could potentially add a bunch of textures to, or including entire directories. And then for each one of these, you can change the compression mode that's being used. So this is using ATC, which is kind of an older compression format. I'm going to switch to a newer one. So ETC2 is made standard as part of OpenGLES 3. And so this shows the original image here, the compressed image on the right, and then this one is sort of a visual difference between the two. And then we kind of come up with a metric based on that. So this is 1.71% different from the original image. So whether or not that's acceptable, you can go with that, or you can like try different formats. Added in OpenGLES 3.1 was ASTC, which is both higher quality and potentially can be smaller than any previous compressed format. So you can try those modes out as well. It has a lot of additional options, and it actually takes a long time to compress, which is why I'm not switching to it. It's a fairly expensive compression, but of course on-device decompression is free. So, but the idea with this is that you can, if you have your artists that are trying to make sure the textures look good in the application, they can use this tool to experiment with different texture compression formats and decide on the best ones. And you can actually set this all up then that this all runs in batch mode. So this tool, it's visual and GUI here, but it also runs in batch mode where you basically just feed it a file that points it to all the textures you want converted, and it will just go through and convert them all and output them either in KTX, which is kind of the Chronos standard image format for compressed textures or any other textures that are compatible with OpenGLES, or DDS. If you have your own tools that you want to incorporate texture compression into, we do include with the SDK a library as well. So that's here. So there's this texture converter library. So it basically just is a lib that you would link to your existing tool chain, and it supports all the compressed texture formats that are standard in OpenGLES and that are supported on our hardware. And then we've linked to a bunch of other smaller tools as well. We do have an application framework that includes some nice things like resource packing and mesh conversion and optimization and things like that, which are all sort of designed for you to pick up and incorporate into your existing things if you want to do that. And I think that's it for the SDK. Oh, I guess the other thing I would mention is documentation. So all of our documentation is in here as well. Most of these are available as PDFs, so you can just launch them from here and get access to all of our best practices and other recommendations for developing for our hardware. That's it.
Cool. So you guys learned about the hardware, architectures, tools. You guys are the best game programmers out there. Cool. So anyway, I think this is basically what we had planned for our graphics and gaming. All the tools that you guys saw are available for free on developer.qualcomm.com, and they do work on commercial devices. So if you have a Samsung, any commercial device based on Snapdragon, basically you can start using those. So you can, in fact, if you go to developer.qualcomm.com, download Profiler, have your game or application on your device, you can start profiling. Cool. So any questions that you guys have? We're going to be hanging around over here if you guys have more questions. But I think that was the last session that we had as part of this workshop. Rick, do you have anything to closing comments or?
No, the only thing I wanted to say is if you guys wouldn't mind, there's a Samsung Developers app. If we might bring to the session, appreciate it. Also, we've got devices available, so anyone who wants to come up and do some safe, hands-on on any of these tools, we're all going to do it. Thank you very much.
Thank you, guys.